Varios caribeños llevamos aquí de clases. De empezar a las 10:30 es que no se me había planteado en mi vida eso. A la universidad. No sé cuándo entrarás tú, pero yo entraba a las... Quita el micro y el volumen.
Okay, so good morning. Let's start. So, first thing I want to show you. ¿Puedes cerrar la puerta, por favor? So first thing I would like to show you is not this, but as you remember yesterday, we set up, well, we had a Raspberry Pi that is on the third floor that has an MQTT and Mosquito server running. So today I'm gonna connect it to the same port that we use for the CNC machine so that remote students can also use it. And just want to show you one extra thing before we talk about wire communications, that is this interface called Notebed. So this is a software made by IBM. It's quite common, built on Node.js that helps to build the flows on a visual way, let's say. So you can make like visual programming somehow with these buckets in here that can make quite nice things regarding dashboards and more other things. For instance, if you wanted to do something like this, in which you can control a process in a web interface with some gauges, some sliders, buttons, grabs, etc. This is easily customizable in here in this interface. Okay. If you want to reproduce it, well, you can use the one in the Pi. As you see, it's in the port 1880. And remote students for now cannot access it, but you will be able to access it. I will send you information on how to access it later today. But basically, you can get in here and make different flows and configure if you want to watch or monitor some processes. And if you want to do it on your own Raspberry Pi, there is also information on how to do so, no, not in this one, but in this one. There's information on how to do so in FabLab VCM projects, learning multi-networking, and in the remote networks repository, okay, or branch. And here is the one that you see up here, which last year we did a session in which the students remotely at home were sending sensor data to a Raspberry Pi located in my house that then I was plotting in this dashboard. And we had all these little gauges and things like this, okay? Also, well, here you have the configuration and things like that. But also there's here some more information about, just to finalize what we talked about yesterday on MQTT, on how to do these things using Python. And you know that I like to be able to do more or less the same things in Python and in Arduino, at least for the things that can apply in a Raspberry Pi. And here is a small example on how to send the same things that you did yesterday, but using Python for MQTT. Okay. So that's it for MQTT. There's no, this is quite simple that you just remember you can subscribe to things or you can publish to things. Remember there were topics separated by slashes that you send a payload or a message, and you have to connect to a server address, and sometimes you will have to use a user and a password for security. In this one that we're going to set here today, we're going to set up a user and a password so that we don't have an open port in the internet that people can send data or garbage to. Okay. Any questions regarding this? This is quite commonly used in the interface part as well. A lot of students end up doing like a web interface that looks like this. We'll also see a lot of things next week with the A-frame processing, etc. But people that have to handle sensor data and that has to centralize it in a node, let's say, end up making a small dashboard to plot the data like this in a web interface. Yeah.
How to deal with data management in the sense like maybe is that SD file, buffer data, sending in that time? Or...
Not really. We can have, if you want, an optional session at the end in the academy, and we can put it as a code club, but it's not in the digital fabrication realm. It's
what we are in this week, the main one to create the data, and then when you can, and
yeah.
plug them, at least storing them in some way on the node,
Mm-hmm.
because from this instantaneous data, or is it like a rate of stored data?
There's a persistence that is normally, well, you can define it, but it's not very large persistence. It's probably 100 points, okay. And then last in, first out. Okay. Sorry, first in, first out. Sorry.
Okay.
Yeah. If sorry.
Okay. Denise, yesterday they asked.
Yeah.
So next question.
So if you want, what we can do at some point is have someone from Smart Citizen in the backend section that talks about a platform, and we use Smart Citizen as an example if you're interested. It's a little bit more complex, but I can say I can send you some guides on how to do this, for instance, on a Raspberry Pi in a small level as well. For that, yes. For this, you need some. For this, you need some concepts about databases, about data flows, storage, and things like this, and maybe a code club session about that would be useful if you want. Okay, so that's that for Node-RED. During today, if I have time, I will send you, well, I will install it in here and send you credentials and things like that, and IP addresses if you want to use it, as well as if you want to use the MQTT server or the broker that is in the Pi by default. Or if you have one and you want to do it as well, instructions here, and you can ask about.
You preview or you
Sorry?
How can you preview?
How do I preview?
Yeah.
Well, I have to put some stuff in here, but if you, once you install the dashboard, actually, let me just show you very quickly. So it's, well, this is npm is the Node package manager. It's like pip, but for Node. Node is a framework in JavaScript that I'm gonna get some more.
And you are able to use the title?
Yeah. And I mean, I saw that there will be same issue. I think I also.
Okay, sorry for that. So Node-RED is installed, system CTL restart Node-RED.
The idea that you practice at the same time, or just to just and then
Yeah.
and then.
No. The idea is that
Okay.
so it's a yes to the second question.
Sorry?
It's a yes to the second question.
Okay.
So nodes, blah, blah, blah. And here, dashboard. Maybe I have to restore the whole thing. Not sure, but okay, to not take more time, there is.
Okay, let's see the one we found.
Okay, well, I'll check it and I'll make it work. There are some issues, I think, here. Either way, it's quite clear, and here on the, let's say, nodes section, you can find dashboard graphs and things like that then you can drag, configure, and when you deploy, this button is to deploy and actually see the thing. You can go to UI, user interface, and then you see the dashboard, and you can configure the dashboard here. But it's quite intuitive. It's not wrong. We can see this later on. Now let's go to the class. So we're going to go a little bit deeper into the wired communication, and then Edu is going to take over and talk about over-the-air communication. Yesterday we talked about different types of protocols, depending on whether or not they are synced or not synced, if they are series or parallel. Today we're going to look at some examples. And the first one of them is serial, or what we normally, when we say serial, we also talk about UART. It's the same thing. UART is the way that is implemented in the microcontroller, and is these nodes here. Some people also call it USART, so Universal Serial Asynchronous Receiver Transmitters. It's the same. It's always RxDX. Okay, there's nothing else. And this is the one that you have already been using for a million times already, serial. You begin it with the baud rate. The baud rate, just to remind you, is the speed at which the communication happens, and is specified as the rate of change of a signal. So serial communication goes in digital, so it has to be either high or low, and it means that the signals are going to look like this. And the baud rate is the rate of the events like falling edge or rising edge. So if we're counting falling edges, it means like 1, 2, 3, and the amount of times that that happens per second is called baud rate.
If you say your baud rate is low, the data you see will be correct.
So, sorry again.
If you set the baud rate to the studio monitor too low, like lower than that, the signal you see.
Yeah.
You get like
Garbage.
data.
You just get garbage because you are expecting data at a different rate. And okay, so what we have to understand is that in any type of communication protocol, there is a encoding phase and a decoding phase. That means that, and let me clarify that. So when you have you're talking between two microcontrollers, microcontroller 1 and microcontroller 2. And here you say you want to send hello. There is an encoding phase that does and turns this into something more like 0100, sorry, something like that. And that is transmitted over the pin here, that is the TX pin. And then here that's connected to, on the other end, logically to the RX. And then happens a decoding phase on this end, right? You receive hopefully the same thing. Ideally, you would, if there's no mistakes on the communication. And then there is a decoding happening so that you understand that this is hello, right? Imagine that you are sending data at 9,600 volts and you are expecting it in here at a made up number at 500 volts. It doesn't exist, but imagine that that happens. So what you're gonna get is something like some data that is not there because you are sending so fast in here, and here you are not getting this one, you're not getting this one, you're not seeing this one. I don't know, it doesn't have to be exactly that. But at the end, the message that you receive is not that, it's something more like that. And you were expecting to receive this. Yeah. So at the end, both of them, they have to be synchronized so that they expect data at the same pace. Otherwise, you're just reading things. As you know, reading something is taking a snapshot of a pin, let's say. At some point, I take a snapshot and I save that in a variable. If I'm taking a snapshot too slow, then I am just getting some or losing some information across the way. Yeah. Now, please close the door. Now, normally in protocols, so this encoding phase happens automatically because in C++ there is a process that we were talking about yesterday that is called casting, that basically does this encoding and changing this string. So let's look at how that happens. It's changing a string into something that is, or a string is an array of chars. And that array of chars is being converted into an array of bytes. And that conversion chars to bytes is direct, and a string is directly an array of chars. And then that array of chars is what you get in here. So this is this in here. So this encoding process happens just splitting all the things and getting the bytes in here. That happens, let's say, on the protocol, and it has to be the same on the other end. when you do this decoding process, that conversion, array of chars and string, normally happens to be something very weird, like something like that. Yeah, because this the encoding phase happens, let's say, in a lookup table manner. So it's of course always this means H, this means E, this means L, etc. And when you don't get that, then you get a bunch of garbage.
One question, answering the definition of byte. One byte, so they put Windows, when you say that this is very that means that the word byte can change of meaning, like one microcontroller is 12 byte and the other one.
No, the byte is always a byte is always 8 bits. Yeah, that is the only thing, or what that might confuse is that there's something called or the system architecture that can be in small microcontrollers is 8 bits. So 8 bits architecture, that is all these microcontrollers that we use here. Some other microcontrollers are 32 bits or used to be 32 bits, and now the big computers and processors are 64 bits. And for that, it means what we do in there is that an 8-bit architecture is able to store registers of 8 bits or 1 byte, meaning that the internal architecture, and if you have been playing already with your registers, as we did in embedded programming some weeks ago, this means that the slots in the memory in the microcontroller are 1 byte of width, meaning the registers are 1 byte. In larger microcontrollers, microprocessors, this is bigger, it's 64. And actually in Windows, when they say that it's 32 bits, it's fake, because it's actually 64, but it's done, it's made into 32, because there's some compatibility stuff in Windows that no one understands why, but they do it that way. But basically, all microprocessors are 64, but that is only related to the architecture. A byte is always 8 bits, and then how the microcontroller stores internally the status of its environment or the memory in itself, which is stored in registers. The length of those registers is what is defining the architecture of the microcontroller. Exactly.
That's the one the way bytes are managed.
Exactly. Yeah. And imagine otherwise the mess that we would have to standardize something that changes from microcontroller to microcontroller. No, at least we agree on that. Yeah. Okay, so regarding serial communication, that is more or less what happens. The idea is that in serial communication, you or some Arduinos even they don't only have one serial port. You can have as many. Sometimes by hardware you have like in the Arduino Zero, which is a SAMD21, you can have 2 serial ports, and they are defined differently. This is the way that Arduino makes it, but you can define this as you wish, and you can have different speeds in both serials.
It's important that if you use, for example, you can have that you're using the computer to the controller with 1 speed, and the controller is using a Bluetooth module, for example, that is also using serial to another speed. It's important that the data is sent from the fastest to the slowest, but not to the slowest to the fastest, because you can miss also packages between the between the 2 communications.
Exactly. Yeah, and this is a little bit like the information theory we talked about when we were looking at sensors. That basically, and if you remember the frequencies at which sensors are read, you cannot read a sensor faster than it actually can give you information. So this is the same. At the end, the Bluetooth module is going to be draining or you're going to be sending information to the Bluetooth module. And if you are asking for information that is not there provided by whatever other thing, in this case, the other serial, then it's not going to work because you are emptying at the end. So I see your face is very confused. In serial communication, there is a buffer that basically imagine that you have these two buffers, and this one is around here, and then this one is around here, but you empty this one at 3 times the speed that you empty this one. So this is at 1x, and this is at 3x. At some point, this one over here is going to be here, and the other one will still be here. So you won't have information to send from here, and this one is going to collapse. So what Edu is saying is that you have to fill up this one in a faster way than you drain it. Yeah. Does that make sense? Well, that doesn't matter the size of the buffer, as if you drain faster than you fill, at some point it's going to collapse. Yeah, that will also happen. So you more or less have to be able to match both speeds if possible. Yeah. Yeah.
There is actually a huge problem usually when you use like long range communication. Long range communication, imagine that you don't have 3x here, but you have an antenna that is like 100 megahertz, super long range. These guys, usually as the wavelength is super big, you have a really small baud rate. We are talking about like 4,800 or less. So actually we need to transmit really slowly the data because we cannot put a lot of information in the wavelength. So actually what happens is usually you can have like a, I don't know, I2C reading like billions of data, and you are sending, for example, if you connect to any computer, you are using a super high speed of baud rate. This can clearly become a bottleneck because as you can have a lot of data and process a lot of data, but actually the speed of the final transmission is really slow. And this all happens not if you have a computer here, but for example, these devices are difficult to wire to, for example, a computer or anything. So actually here, this guy could be a Bluetooth module. Actually, you can connect your computer wirelessly to a Bluetooth module that is something that is all around, or a Wi-Fi, and then Bluetooth talks to your controller, and your controller sends information with long-range radio really far away. For example, in the rooftop, we have a LoRa. We don't have a Bluetooth connected, or Wi-Fi, it's not connected to Wi-Fi, but we can have like this working as a bridge. This controller just being a bridge between two different types of protocol communication. In this guy is not doing anything, it's just making the bridge between Wi-Fi to LoRa. LoRa is like long-range communication radio.
Are you going to talk about LoRa later?
Not too much, but
Okay, because you cannot clear my drawings.
no. Where did you go, by the way? Looks nice.
I had this question.
Where? That's Sublime.
Yeah?
Sublime.
Hola.
Yeah.
We're talking about like wavelength and wave frequencies, basically, and how they affect how signal propagates over the air, especially when you look into the overall circuit, traverse circuit. So that if you want to say if you want a signal to go through a wall, its frequency to be quite low for the wavelength, and it's not be blocked by the side of the wall. But that affects as well, like how fast you're receiving data.
Yes.
Because so when you're talking to GPS satellite, basically, you said the wavelength is very, very low.
It's right, it's low.
So is that one of the reasons why it takes some time to triangulate?
No, that is because you need that's GPS protocol and how it's to determine stability on the link. On the link. To get a GPS location, it's not GPS, one GPS.
Yeah,
The minimum of 3. but actually that's not true. The minimum for the GPS standard to have like accurate positioning that around 3 meters is 6.
Okay.
To get a good positioning is 9. To get a really stable positioning up to 1 meter is 12. And usually you want to go over like between 9 to 16 or 18. But that depends on all the sides of the world. For example, in Spain, we are over most of the trails of the GPSs. So actually it's really easy to get locations of 16, 14 in Spain. But I have seen in some part of the world, for example, in Siberia, it was impossible to acquire more than 5. So you never get what is called a GPS block. That is actually locked in place, and you have at least 1 GPS of backup. That means you have 7, 6.
There's also, if you want to read about the EMEA GPS sequences, there's also this concept called fixed quality, which is basically related to the signal strength and how many GPSs or how many satellites you see. So fixed quality of 12 satellites is around 3, which is what you want for a good location thing. And that's standardized, like fixed quality 0, 1, 2, 3. 0 is you're not located, 1 is very poor, 2 is okay, 3 is fine. About data rate, I recommend if you want to read information here in the Thin Network. It's a community and an open project about LoRa, and they have quite a bit of quite good documentation about LoRa, but also about radio frequency in general. And here they basically talk about, in particular, the LoRaWAN protocol, that the things that you can click. We have a node for the Thin Network upstairs, but I don't think we have any LoRa antennas. But basically, these are used to transmit low range, very. Yeah, but we don't have antennas ourselves.
But we can make an antenna.
Okay. So
the receiver model is maybe.
So what I would encourage you, if you want, is to also have a look into this. It's quite common if you are looking into sensor data, especially because you want to send data without having to rely on Wi-Fi or, like, let's say, short distance communication. And this is able to get to kilometers range with a reasonably okay package transmission. It's not, there's some standards on how much data you can send per package and how long you will get. And also to be part of the Signal First community, you have to be, let's say, not taking over the network by sending too much data. So you have to, let's say, leave room for the other people to also transmit. But still, there are good lessons here in the LoRaWAN documentation. And basically here they talk about transmission powers, bandwidth, and spreading factor on how far it basically gets. Okay, and in here they basically specify, and in here you can read more about it. So that is for serial communication as well. You can define it by software for the microcontrollers that don't have serial communication by hardware, or that you want to, for instance, have 2 serial ports or 3 serial ports in the same microcontroller. For instance, imagine that you have an Arduino, whatever Arduino, I don't know, that has 1 or 2 ports, and you want to connect, I don't know, a Bluetooth module or a RF module that talks with serial, or that, so you can make your own serial port defining the RX and TX pins, and then use it as if it was the normal here DT1. So you use it as if it was a normal serial beginning as a serial communication. The only thing is that now you call it BT1 instead of serial. Okay, and the rest, the same applies. In this case, for instance, what we're doing is just doing a bridge between serial port on the computer and a Bluetooth module that reads on the serial communication from the USB and then sends it over as an AT commands to the Bluetooth module.
on our video, want to get back this information
Sorry.
on our video, the ID. If you want to get back the serial information of this of the software serial, how do you fix the normal setup?
No, of course. So if you cannot, so this is an internal serial that will talk to something else.
Okay.
So those are other pins. If you wanted to do that, you will need to, if you wanted to test it, you would need an FTDI or USB to TTL, but you cannot connect things as a Y. So
Internet.
So exactly. So in here, imagine that you have your microcontroller and you have, oh, that is very annoying. You have your USB ports and you have, let's say, the two pins that you define by serial. So this is the USB and this is the normal serial println. No? And here you imagine you have RxTX by software serial. Out serial. Right. Serial. Blah, blah, blah. So that's this one. So this one talks to your computer. This is your amazing laptop. And this one is meant to talk to something else, right? For instance, I don't know, Bluetooth or an antenna, okay? If you want, if you want to see what's going out in here, you can use a FTDI cable and send it to this computer, and then have, if you have extra USB ports, then you can see it in here, but you won't be able to have both connected at the same time. Serial communication doesn't allow to have these splits. So either you go this way or you go that way, but not both, okay? And here, an FTDI or what we saw yesterday, USB to TTL, which is the same thing, then allows to connect and see that this software serial is working, but you won't be able to have both connected.
Usually for configuring this kind of devices, if they are done, let's say, to work out of the box, most of them, they configure something that are called the AT commands. That is a super basic set of instructions to configure different baud rates, different speeds of communication, the clock frequency. Like let's say configure basic setup of the board, but not the main program itself. Like for Bluetooth modules is widely used, for Wi-Fi modules also widely used, radio modules, especially for modules that is for usually wireless communication. But some devices that are not just for wireless communication, they also use AT commands. Here you have a problem that if you use software serial libraries, usually as the pins are not, you're not using dedicated pins for serial, they are not as fast as hardware dedicated pins. So you're constrained to slow baud rates. For example, I just checked the documentation and the software serial library of Arduino. They say it works up to 115,200 baud rate, but actually it's not true. Like I know that on the highest, around those baud rates, it has a lot of instability. Actually, there were like 57,000 and lower.
Yeah. Okay. So now that's true. That is it. That's it for serial on Arduino side. In Python, super easy. PySerial, import serial, define the port, define the baud rate, create the object, and then read. And that's it. Okay, very simple usage. I would also recommend if you want, if you are interested on doing things with Python, You can check Smart Citizen tools, serial tools. There is two classes called serial device and serial worker. Serial device basically helps on the setup of a serial device using Python. Let me just put this in the chat if anyone is interested. But basically, it has a lot of methods to set the serial communication, talk to the device, read all the buffers, etc., flash it, streaming data from that into a CSV and things like that. And on this one, it's called a serial worker, which basically opens an instance of the other serial device object and does that in an asynchronous way. So if you are making an application, for instance, that you want to be reading into CSV and then plotting something, you want the data being streamed into CSV no matter how heavy your plot is. So that happens in an asynchronous way, and then your plot reads from the data, but it doesn't go directly into the plot. Let me simplify that. So if you have your Arduino and you have your laptop, you are connected using USB. And here you have a Python script that reads information, import serial, blah, blah, blah. And you want to not just do that and read it, but you want to also store it. So the way you store this is you take it and you send it, for instance, to a text file that can just be this is .py and this is .csv. And then this can happen in what we call synchronous way. And then imagine that you want to have a plot in an interface. Yeah, this is a fancy plot. So you don't want that this script, since you have, so imagine that this script has this communication here that is somehow fast, and this that you don't want to lose it. So this is a critical. I don't want to lose data. Right? You don't want to waste any data, and this flow you always want to guarantee from here to the file. You don't want to miss anything because this is NASA and we have to keep all the data. Then this happens in this way so that you never miss anything. And then this plot in a synchronous way, so meaning in a periodic way, takes data from here and plots it. But you don't do from here plot and CSV data. You know what I mean? You first store it, make sure that it's stored, and then plot it. And you plot it using an asynchronous method, let's say. So in here you have some methods as well to do that, and basically runs a stream to store it in CSV, and then be able to plot that thing into a nice graph. Okay. Any questions? There's something in the chat.
That's also feasible in Arduino.
What exactly is feasible in Arduino? Sorry, Lynn? To store in CSV? No. Well, you could if you had an SD card, and if you could do it also
In the ESP, you can.
in let's say, so storing in the SD card normally is going to be using SPI communication. So at least you need SPI pass, and because of that, you need a high speed and high memory microcontroller. You could do that, yes, but it's not going to be an easy, super, or it's going to be a somewhat easy thing if you know what you're doing, but it takes a little time. But if you want to do it, I encourage you to go here. And basically, there is already a device that does that and has stored SD card and saves data in CSV. That you can review the code. So, CSV. So in these lines in here to here, we write on a CSV file the data that we have that we're reading from the sensors. This means handling an SD card is it needs, or handling a file system is not an easy thing, if especially take care of if the file exists or not, if you are overwriting a file or not, and being careful of not crashing the file. And here, Victor especially takes care of that, and also price that in an order fashion. He just was passing by. Yeah. No. Okay. So basically, here like we write that into a CSV file, and the best thing here is to just use the memory that takes care of the management of the and that you write. An example is within here, but as you can see, it's not a short piece of code. Let's hurry it away. But you can do it. Anything else? Someone is unmuted. Lynn, mute yourself.
Es que mi memoria es PIPs que se puede pero es compleja. No me
Sí. Yo no sé, no quiero hablar de eso, pues no sé. O sea, no
sé que se
hablo.
puede. Irse con el lo hacen. Pero
no lo usan. O sea, yo no lo he hecho. Okay. 2 more protocols and we're done. I2C. This was we already know about this one. You tried that yesterday and we had some issues. I had a nice conversation yesterday when we have lunch about this thing of masters and slaves, and in electronics. And I don't know, maybe at some point we can chat up. But there's a huge movement now in the open source community to avoid talking about masters and slaves in open source. That basically doesn't want to use, doesn't want to use this terminology as it can be reminding of slavery. Honestly, from my point of view, it's a valid point, but I also think that open source hardware. Yeah, so if you want to read and you can have your own criteria about this, that is, I have nothing wrong against it, but they are proposing some changes in here. And even they are changing MISO and MOSI, that is mastering a slave out or master out a slave in, into other things. My personal opinion is that as long as you are aware of what you're talking about and there's no connotation that of slavery and any racial connotation, I think it's fine. But otherwise, I'm more than happy if you name these things or this way in your file page. I really don't care. It's just a personal opinion, but my opinion is that as long as you are aware of it and that you are not actually supporting slavery, there's no problem for it. But that is a totally personal opinion. So maybe one day we'll change this as well. But basically what we are saying is that we have two microcontrollers, and that one that is managing the thing and the other one is obeying somehow. The one that is managing is requesting data and is also able to start communications with the others. The ones that are being, let's say, controlled, they can't start communication unless they are requested to. That means that you have basically a bus of devices that one of them is like the director and the other ones are just being asked things for.
I saw in I2C that you cannot see what exactly? It's like twice the EA or those two wires, and I don't know how the data is.
So that you can have two I2C buses, or yeah, you can have that, and you can define that by software as well, or if the hardware has two I2C buses, you can do it.
What are like set of I2C wires, or one set of I2C wires, and the data are separated, and I don't know.
So no, it's two separate buses. So you would define two wire interfaces. Yeah. Yeah. Yeah.
In essence, sorry, I2C is like a serial network, right? Devices being different.
It's a what?
A serial network, a network in serial, so multiple devices at the same time.
It's a bus more than a serial. Serial normally means that is something that is that goes more in this fashion. So you have one and then another and then another, and data goes into here and then inside of this one and then in this one and then to the next. Okay. But what we are saying here is that we have something more like, no. That we have something more like, instead of that, we have something more like this. And each of them connects to the bus. They hang from the bus, let's say, but they are not. If I remove this one, the rest is to work. Okay. Yeah, and in the other case, if they are in series, it's like the Christmas lights. That if one fails, then the whole thing after that is fucked up. That's it. Yeah. So things about I2C that, well, some of them we discovered yesterday. ESP apparently doesn't like to be a slave. I don't know what the connotation of that means, but basically there's like some issues there, and you, Adrian, were making quite a good research on that yesterday. Just going a little bit deeper into the things that we didn't talk about yesterday, besides addresses and this type of things. There is quite an important note on communication and how the protocol is established. So imagine that you have two I2C devices that have the microcontroller in here and another microcontroller in here. There are two considerations to take into account. The first one is the wiring length. So this one, you have ground, you have ideally voltage. And actually, okay, let me clarify this better. Let me start over. And let me do this. Option number one, okay, or case number one, is that we have two I2C devices. One is being powered by a USB or whatever, and then this one is powering this one. Okay. Power is going from here to here, and this one doesn't have power. So I2C bus is powering the device. Okay. Well, the bus is not powering actually, but the device is being powered by the main one. Okay. Thank you. That means that both microcontrollers have to talk at the same voltage level, meaning that if this is if this is 5 volts, this other one has to be 5 volts. Okay, because the data line and the clock line, they need to be at the same, or at a certain voltage, but it's normally going to be at the voltage level of the microcontroller, and that requires that both of them talk at the same voltage level. Okay. Option number 2 is that we don't have that situation and that we still are powering the device using USB, but that instead of having two of the same kind, this one is 5 volts, and this one, unluckily, is 3.3. And for this, we need
separate 5 volt communication, and they have the same ground.
yeah.
The 5 volt is not exactly the same voltage, but
Yeah.
That's why you connect the ground together to avoid noise.
Okay, so I connect the ground, but maybe one will be 5.2 and the other.
No problem.
Okay.
So if this is looking at that, at the end you have to think that this is a digital signal. And the digital signal is going to be either high or low, and the threshold between high and low is defined. So imagine, yeah, perfect. So imagine that this is the threshold for the signal to be high. It has to be something like around here, and for it to be low, it has to be something around here. Okay, so if you have a signal that is undefined, maybe something around here, you have a problem. But if you have a signal that is here and a signal that is here, for this is fine. But the important part is that it's not that the signal is here with respect to something, and that something is ground. And then it has to be respect to this line, which both of them are over the threshold.
Hopefully, right? Unless the body is really, really, really well designed, you are never in zero.
Sorry?
Unless the body is really, really well designed, you are never in complete zero voltage. You have like micro voltage coming up, and you have something that is doing like this. And if in the high also happens the same. The variation is smaller because you're already like giving a bigger blast. But in the zero that you don't have, in theory, you are not giving anything. Just the electromagnetic field is moving a little bit of electrons through the cables, enough to give this a small what is considered noise.
Okay. So now let's imagine that we have two at a different voltage. We have to share ground, that for sure. We are powering, let's say, the 5 volts one. So we are powering this one. We are powering this one using USB. And then what do we do with the other one? Because we have 5 volts, and this one works at 3.3, right? So we can have several options. In this case, what we could do is always power this one as well at 5 volts and have a voltage regulator in here. So an LDO that we already talked about, basically bringing 5 to 3.3. But that we cannot use that for the communication because communication has to go on both sides. And an LDO only goes from high to low, but it's not able to convert low to high. Okay. So in here we need something that is called a level shifter in the middle, which is here that is able to convert both signals to in a bidirectional way, right? So in this case, we have our SDA and SCL lines that go, oh shit, that go from here, and then they go here, and then the other way around. They go here and go here, and the level shifter takes care of managing that. But who powers? Do we share power in this case? Well, it depends, because normally this is going to be a cable that is going to have 4 lines: ground, data, clock, and power. And if we share the 5 volts, we have to make sure that the pin that we're sharing it into, so let's say that it goes in here, then that there is, if this is 5 volts, there has to be an input into the LDO so that we go to 3.3. Otherwise, we shouldn't do this. And we should either feed this one through USB, go through the LDO, and then to 3.3, or that's it. No.
And actually, here you have something that you are missing. Is this guy also needs to have the power?
No.
The level shifter?
Depends. There are passive level shifters that one needs. So there are some level shifters that there are microchips that needs to get the voltage reference, but they don't need to be powered. The thing in the level shifter is that the level shifter will work with, let's say, actually, let me show you a board that I'm working on. It's going to be much easier.
Live demo.
So the level shifter basically doesn't need ground, but it needs to know the voltage level at which it's converting to. And that is happening. Okay. Let me clear. The level shifter is basically this. That imagine this side is a 3.3, data and clock. This is 3.3, and this is basically a MOSFET. And here you have 5 volts and the data at 5. Sorry? This is data and this is clock. They are separate. But this is 3.3, so this is 3.3, the same as this one. And this is 5 volts. Or it can be virtually anything, actually. You have this setup, and basically you're converting this line from 3.3 to 5, or from 5 to 3.3. Okay? Like PWM? No, this is not as simple like that, but the idea is that, remember that the MOSFETs, N-channel MOSFETs, need a voltage difference between gate and source that is higher than the threshold of the MOSFET. And honestly, I don't want to say any lie because this is like a complex thing. But with this setup, you manage to control the opening and closing of the gate depending on this data line or this data line, and manage how it opens and closes so that you transcribe this with these 2 pull-ups in both directions. Honestly, this is type of thing that you read in an application notes, and I don't want to say bad things because I don't know exactly how it works, okay? But it does work. It's the general way that these things are implemented. Some of them come in a SOIC, so system in a chip, that also have extra things like an enable pin and some other functionalities. So that are, for instance, the one that you might have put into the SPML, the purple one, that has some extra stuff. Okay, but you can build your own with this, basically. Start. Yeah. Well,
Can you just explain that why we need the double
and an LDO.
LDO?
Yeah. So you have the situation in which you have 5 volts on one side and 3.3, meaning that this microcontroller here is powered at 3.3 and this is at 5. Ground is going to be always shared, but the communication is not able to happen in this fashion because this one is expecting 5 volts and this one is expecting 3.3. So in the middle, we need to put something that converts that signal, and that is called, or that shifts the signal, and that is called the level shifter.
It does it both ways.
It does it in a bidirectional way, yeah.
And this is for the data. The LDO
That's-
is for
The LDO is for the power.
for the power.
Yeah.
Okay,
Yeah, and the LDO basically what it does is that imagine that we have let me draw in here. So the LDO basically does, imagine that we want to have 3.3 and this is the input volt. I always get confused with this. So this is input and this is output, and this one is 3.3.
you have the USB in the 5.
And the USB is giving 5 in here. So the LDO is going to convert down to here and giving you 3.3. If you have 3.3, it might not work because normally if you input 3.3 into the LDO, normally LDOs have 0.9 to 1.5 range of voltage that they need in extra so that they can make the conversion. So around here is your limit, and above it's fine. So any voltage above that is going to be regulated at 3. Any voltage below that is actually, well, it depends. Might do like this, or might shut down. I'm not good.
But I have 3.3.
Yeah, exactly.
But happen, for example, let's say you have a faulty power supply. You have faulty power supply and you want to regulate if your power is 3.5 and you 3.3. You need to really check the LDO because a lot of them, they have that threshold. And if you actually run all down that threshold, they overheat. It's weird actually, and they overheat and they self-burn themselves.
Just another question. In this case, for example, the 5 is also is powered separately.
So in this case, there could be 2 options. And the good option here, in my opinion, is to power this with 5 volts. So this one comes with 5.
Yeah.
That is a 5, not a 3. And then you have the LDO.
And the other one powered separately with the 5.
Exactly. Yeah.
Because when you power the 3.3 one, it passes through the LDO and converts
Up to 3.3.
to 3.3. If you're powering the 5 through the 3.3, it also has to pass through the LDO.
So if you're powering
the right to the right.
Yeah.
Yeah, if you're powering this one,
it has
the second one also through it
from here.
from here.
Yeah,
Okay.
you could.
Those
But
are
that, yeah, but that is happening before. The thing about here is that you have to take into account cabling. So how many cables go from one board to another. That is also like intuitive, that you don't have power going from one to another from a seemingly 3 point or lower voltage board to a higher voltage board. That doesn't really, it's not a very intuitive thing. and the other one is current, because here you might have a power supply that gives you, I don't know, 200 milliamps. This LDO is rated at 100 milliamps, because here you have whatever it is at a 50. So you have some safety margin. So it means that more or less here you have at maximum 150, but to be safe, let's say 100, because this could change and there could be peaks or whatever. So then you have here a limitation of, again, 100 milliamps of usage, which is fine. But if you have some extra things, that it doesn't mean that you won't be able to use it, and it doesn't really make sense to have a power supply of 200 milliamps to only be able to use 100 in a board that might as well be powered for 200, unless that is very minimal. I mean, if it's for sensors and things like this, it's okay. But if you want to run things like motors or whatever, this is not going to be 200. It's going to be more like 2 amps. And it always depends, but it's more about taking into account all these considerations, not just as simple as connecting things, but also taking into account that.
Also, power supplies that milliamps or amps is what they can max out, not what that they are constantly giving. So they don't only give what you ask for them. Actually, if you rate, if you are you need 200 milliamps and you 200 milliamps, what you're doing is making the power supply work at the maximum all the time. That might lead to like shorter lifetime.
Exactly. So that's it. We have 2 cases then. Both the boards are powered at the same voltage, and then the communication happens at 5 volts. Or we could have 5 volts and 3.3, or whatever. And you need a level shifter, and you also need to take care of the powering of each of them. That is more into the field of electronics design, but it also applies, or it's needed in the level 15.
Can we use voltage dividers as level shifter?
No. A voltage divider doesn't amplify.
No, the opposite. To reduce. If you're working from 5 to 3.
Yeah, but then the communication is always in I2C will always happen on one direction, on both directions. Sorry. The thing about since you only have a data line, you could have a voltage divider in the clock line. I never have seen that.
It's a silly question, but
No. I've never seen it, but I don't think it really applies in this case, because imagine we have ground here, and then we have our clock that is being managed by I'm sorry, I'm just going to use the terminology, master and slave. I mean, you don't know, but I just tell you, I'm not in favor of that. But basically, that this is going to be that this is like that, right? This is 5 volts. And you are expecting here 3.3. So yes, you could use, since this is the one that is managing the clock always, then you could use a voltage divider if you wanted to make this into this in here, right? So, because you only have to bring down, but it doesn't have to go up that way. Now, if you want to send, or if you have the data line is not that we are sending data like just like this, but actually the data line is more or less like that, and either this one. So sorry, this is the data line is 5 volts, and this is 0. So the data line is going to be up because you have a pull-up resistor. Since you have this pull-up resistor in here, the data line is by default high. So either one has to be able to pull down the data line. And by that, it needs to, and that's the way that the communication happens. So either this one or this one will bring the data line to ground, pulling it down, like defeating this pull-up resistor. And that can happen either from the master side or from the slave side. If you have a voltage divider, what happens is that you have this, and then this, and then you have the 3.3 here, and then the 5 in here. And this is on this side is the 3.3. When you want to pull it down, basically, if you pull this one down in here, if you pull this line down in here, this one is going to be pulled down. But if you pull this one down in here, it doesn't mean that you're going to be able to pull this one down, because you still have this resistor and this other resistor, and you don't know exactly what's going to be the ratio between those. So
What's the one, sorry? You said you don't know that?
the ratio, like if that is actually going to be, if this is going to be able to pull down with this. So it's much easier just to do it with a level shifter with that matter. Also because the transition, this transition has to look like that, and it shouldn't look like this. And that is linked to the amount of components that you have in the line. And to simplify that very quickly, and stop talking because I'm talking too much, is that when you have the data lines, when you have the data lines, sorry, the data line is going to be red now. Well, no, let's do it. So you have this, and you have this again, and you have SDA and SCL, and then you have the famous pull-up resistors that look amazing to high, right? So these two are pull-up resistors. We're saying that basically the pull-up, the microcontrollers on each side have to be able to pull down the line. And to be able to pull down the line, they have to be able to compensate this resistor so that they can bring it down. And that resistor, that's why it's normally very high, so that it doesn't put so much, that you don't require so much current for it to be pulled down. But it can happen that these lines, since they are cables and they are made out of physical material, they have some sort of capacitance, which means that they act as a capacitor. And if you have a capacitor, you know that a capacitor, when it's full, it doesn't go like that, but it goes like that, right? Because that's the way capacitors work. They store some energy for a very short time, and they smoothen out edges. That can be beneficial to remove noise, but in this case, when we want a sharp edge like this, that is not good. And when you have a very long line, but you have very high resistors, it can be that your signal, instead of being something like this, it becomes more something like this. Okay, because you have a lot of capacitance, and that is related to the load. So the capacitance, inheritance capacitance of both microcontrollers, and how long the lines are. Meaning that if this line is super long, for instance, normally is around 20 or 30 centimeters, the capacitance is going to be high enough so that your signal is not going to become let's say, a standard I2C signal, and it's going to be a bad signal, and you're not going to be able to establish communication because the edges are not sharp enough. Okay, and basically you have noise. Another thing that can happen is that in here you have some breaks because you have connected into a breadboard, or you have like a lot of things that basically act as reflectors. And this happens the same as when you are on the sea, and there's like the waves that come in and they crash, and then some of them go back, right? The waves go in and reflect because they just hit something and come back. So this is exactly the same. When you are sending something like this and you have a lot of changes, if these changes are not good contacts, some of the signal is going to be reflected, especially at very high frequency. So this signal is going to come back and it's going to overlay onto this one. And basically when it gets here again, it's going to overlay again. And this signal, instead of being that, is going to become something more like that. Yeah, and that is noise, basically, which doesn't start communication. So I2C and SPI, they both need these considerations. Take care into the length of the cables, how many jumps you have, soldering things in general in a communication protocol that is normally high speed needs like good connections, taking care of soldering to avoid reflections, and also to have a lower capacitance on the line so that you can handle or you can have a clean signal. If you have long signals, that is not the end, long cables, that's not the end of the world. You can also change the value of these resistors that we normally tell you that are 10K, but that is, sorry, 10K ohms by default, but that's not the case. That is like a standard value, but they could be as low as 1000K or even lower depending. But normally, these values are more around something like 3 to 5K if we actually calculated how it should be.
So, for the local plan, I would like to see that.
Yeah. So if you wanted to do this with wire, it depends on what. The first question would be, what do you want to transmit? If you want to talk, if you want to send data, or if you want to just send voltage, like a high or low. If you want to send data, you would probably do something like, let me clean this. And if you want to do it wired, you could do something that is a bridge node. That, for instance, this one talks with this one I2C. And then this bridge converts from I2C to something like, I don't know, serial or Ethernet, or it does have, but you can amplify signal or, well, USB, sorry, not serial, with
7 meters,
amplifiers.
more or less, depends if it's, but you can consider up to 7 meters. That depends on a lot of wire quality, if the cable is shielded, for example. So with I2C, if the cable is shielded, it's good copper, like thick one also. That's what makes the cable construction more expensive. For example, that's also what some HDMI cables are like 200 euros, and other ones are like 5 euros. Shielding, material quality on build construction, and if the cable is twisted, it's just elongated.
And here, a very common setup, imagine, not for these lamps, but imagine that you wanted to do something like very long distance, is using Modbus to RS423, 485, 45, or whatever, bridges. Modbus to oh, well, sorry, this is to LoRa, but it's to use a module that basically receives Modbus or Monopoles, converters that basically Modbus we could assimilate it as I2C in an industrial sense, but that we converted to something else like RS232, serial communication, 45, etc. That you can draw, you can put longer cables, and then you have a converter that talks to your microcontroller on one side, very long cable, Ethernet or similar, another converter, and then what you talk on the other end. And that is quite common for more, let's say, high-end, or not high-end, but long distance things. As well, if you wanted, if you do this, there is a lot of these things as well that basically convert, for instance, HDMI cables that are not HDMI cables that can be 20, 30, 50, there are, but they're, or I don't know if there are actually, but they're going to be quite expensive and signal is not going to be good. So you can use one of these that converts into Ethernet, and then you can draw a 50 meters, 100 meters Ethernet cable, Cat6, and then on the other end you convert back to HDMI.
For example, for let's say this space, we have like lots of sensors in the space. We will use like RS 485. It's really robust and I think can go up to 100 meters or between 50 to 100 meters, depending on the cable quality. And it's super steady, like the amount of data transmission is lower, but also needs only 2 wires. It doesn't even share ground and voltage, just 2-line data.
Both the voltage in my board will table, so there is no protocol, no nothing. You don't know how to do it, that's just the internet.
I mean, you could do either. The thing is, it's all about data length. Sorry, data length, cable length. The thing is, at the end, each cable is always going to be a resistor. Why can't I? So imagine that you have a cable and you have 5 volts in here, or you're reading something in an ADC, and you imagine that your sensor is on this end and what you're reading is here. Since this is like equivalent to a resistor, at some point there's going to be some voltage drop. If this is too long, since the resistor is basically in ohms per meter of cable, you want to reduce the ohms per meter, but if you have very long cables, that is going to be an effect. If you wanted to, so the idea would be that you move this as close as possible, and then you don't have this problem. And then that if you have to communicate between 2 things, those 2 things, ideally, if you are using chip-to-chip protocol like I2C, SPI, etc., that they are also close to one another. If you want them to be far away, you put a converter, send it, and then send it, or just use Wi-Fi.
Yeah. Also limited by the frequency on which one is sending.
Yeah. Like how often?
Region, like speed and distance, instead of certain speed and those two.
In I2C or sorry, no?
No, Ethernet. Ethernet has like a speed rating.
Yeah. Yeah.
20 meters, so you can set at X hertz.
Yeah, but compared to the sensor data that we are sending and the bandwidth that we're going to take, it's going to be ridiculously high. So you won't have to worry about that using this type of protocol. Last thing about
just for example, just check for the maximum length, the RS 485. It says 10 meters maximum at 35 megabits per second. But if you reduce to 100 kilobits per second, it's 1.2 kilometers. So it's clearly influenced like the speed of transmission.
What else? But it's kilobits per second, which
Yeah.
is, I mean, it's insane how much data it is. Talking about, well, libraries, we talked about wired yesterday. If you're using ATTinies, especially because of memory size, there's TinyWire S and TinyWire M for slave and master. They're gonna have to change the name too. And they are done like that because they don't have ATTinies, they don't have I2C on hardware. And some of them, they have to define this protocol that is called two-wire interface. So if you're looking for information in the datasheet or other libraries for ATTinies and things like that, sometimes, I don't know, for the new series that you were trying yesterday with the 1614, but for the old ones, you have to use it with TWI, which is two-wire interface. So if you don't find I2C on ATTiny 44, look for TWI on ATTiny 44, because that's how normally people implement it. And basically here, you define it by software. Because these are not, it doesn't have a bus on an I2C bus in here, and the functional diagram doesn't exist, and you just do it on the pins, and you do it by software. In the process that we call bit banding, which is basically we just send bits very fast, high and low, and by that we just simulate I2C. Okay. And almost done. Okay, well, just one thing you can also use in Python if you're looking into doing it on a Raspberry Pi. SM Bus is a good library, and as well, if you go to multi-networking, but not in this year, but in local Raspberry Pi, here you have an example as well on how to do it on a Raspberry Pi using an I2C sensor that, in this case, we're using a library, but that you could also implement your own communication for. You have an address as well, and this is, for the case of commercial sensor, it's better to look at the library, but in here, you have the address and I2C, well, in this case, it's again a library, but you could use otherwise the SM bus and read data from the bus in blocks, from the addresses, and in this case, you would have to do the bit shifting that we looked at some weeks ago. You remember that? The bitwise operations that we were saying, we move the bytes and then we OR and 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 things like this. So you would have to do that because there's no library taking care for it. And if you're reading, for instance, 8 bytes, you would have to get byte by byte. So you get one, you put it here, and then you take the next one. You take those 2, you put them here, and then you get the next one. And then you take those 3, you put them here, and you get the next one. And at the end, you have 8. So that's more or less the process that you're doing here. You would have to do that as well if you want it in your Arduino, if you don't want to use a library for a commercial sensor. If you're using I2C and you're sending more than whatever amount of data you define. Yeah. Does that make sense or not? Okay. Okay. I don't know why SPI is in here. I'll edit this, but SPI, as in for protocol, I haven't implemented it, or I haven't used it in a pipe, but you can do as well. But basically, in terms of library, or in terms of, first of all, SPI is not as common as I2C. The library in Arduino is called SPI, and it's kind of a simple way or protocol to use, but it's difficult to implement. And in this case, if you are going to ever use SPI in a library, I would encourage you to look, in your project, check before if there are libraries for whatever you're using, because SPI is a little bit more complex than I2C in terms of instructions. But in here, if you look at it, it all works the same way. SPI begin, in this case we call transfer, but and you transfer information or bytes, bytes as in charts again, and it's the same. It's basically the same idea as in the other ones. But normally sensors that use SPI, they are a little bit more complex, also because they look for performance, as SPI is a more efficient protocol that works better at higher speeds. So higher speeds, more performance, more complicated, look for libraries. Sorry?
The library was for I2C. Then I2C, the port, the address.
Okay. Well, I don't know. I have only used Esp Bus, but I guess now probably there are more libraries. I don't know. Is this a library from Adafruit or something, or is a general one? Okay. Okay. Yeah. Yeah. So in that case, honestly, this is a little too much. But honestly, whenever you are going to use a commercial device, sensor, screens, other microcontrollers, etc., always look at whether or not there is a library already implemented for it. Because, and let's look at this very so this is the data sheet of microcontroller of an ADC that we are implementing now. And in here you have here you have quick start guide talking about registers, reading registers, configurations, and input output codes, resets, etc., etc., etc. You see that is not a short set of instructions or registers, and that is just to read an analog voltage. So some people that we like them because they do things open source, but have done this and implemented these things. So in this case, Adafruit, for instance, they have implemented how to talk to that ADC, and we basically use their libraries, of course. I mean, even Victor that has done this a million times, he doesn't write normally his own library, unless it's a super weird thing that no one has ever used before, but that's not the case. In here, for instance, we also see these registers that were on the data sheet are all in here. And these things takes a little time to write, so use a library. and better use something that has a library behind it, because you're gonna suffer less. And you want to minimize your suffering levels in life, ideally. And that applies to anything, to libraries and sensors, or to interfaces, or to, I don't know, whatever, or data management or modeling and things like this. And that's that. With that, I don't have anything else. Well, I have something else. And yeah, and I was thinking about this yesterday, and I will include it for next year. That is, if any of you is doing something with music instruments, or if willing to do something with music, it would be cool that you work using MIDI. MIDI is a standard that was born in the 80s as an agreement between different companies that were doing music devices, like synthesizers and MPCs or amplifiers, things like that. That basically they agreed on a protocol so that they all could communicate, and you could connect a synthesizer with whatever, and then a pedal, and then something like that. And basically this sends MIDI messages for controllers and synthesizers, and you can implement that and use that in Arduino. It's not that very complex to use, because MIDI is kind of a simple protocol. It has basically channels. So you define a node, which is depending. There's a standard, but it's a node, as in the piano or in the guitar or in the drums, etc. You define how fast that node goes, the volume of that, and the treble, which is if it's like made longer or shorter, and it sounds like a little bit like or things like that. And then you can implement that in Arduino. Imagine that you were making a keyboard that takes an Arduino, and then with USB you send that to a synthesizer. And that synthesizer takes those MIDI notes and plays, I don't know, actual piano, when you touch a keyboard, or you play a drum, or you play a guitar, etc., depending on the sound forms that you use. Which is, I think, kind of a nice way as well. And this would be, it's a protocol that is normally wired and is used in music in general. And it's kind of
For example, if I have one listening to the music, in the sense that if I have an input that's listening to the rest of the music, then transfer those notes to the light, for example. I'm going to say whatever. If I touch music that has a BPM then put the lights.
Yes, you could do that, but MIDI is a way to encode music, but not a way to decode music. So you can, let's say, have an instructions file that says this node and this node with this timing and this speed, and that MIDI will understand that and convert that into music, but it will not get music and convert it into notes. So you will not have to, you need to have that layer of communication of MIDI. So the node that is generating the music also has to send the MIDI to the lights and not get the music converted on the lights as it listens to it. You have to send it somewhere else. Okay? As a side note, and this is just for fun, you can also play music using Python. And at some point I have done that with a generative music script that makes, you can take MIDI music that there's a lot of people that liked Aphex Twin. I like Aphex Twin, and it's a like electronics music composer, and a lot of people has gone or converted that into MIDI. This is how a MIDI file looks like, just so you see. well, this is a binary MIDI file, but let me show you. So this could be the definition of a song, actually from Affix Twin, that you say what the note is, what is the MIDI code for that, how fast it's played, how long, etc., and that defines a whole song. So you could encode this, and at some point I did something that basically learns from that file and plays music endlessly. So basically makes a small model of the music, and then you can generate music that looks like that one or feels like that one forever. And one important thing here, if you want to do that as well, is called Fluid Synth. It's a library that makes a synthesizer on your computer. So a synthesizer is, assume that you know, that it's basically something that takes MIDI notes and takes a sound font, which is just a library of sounds associated to notes. And when it receives a note, it plays a sound. And it also modifies certain things on the sound, like the treble, the speed, the volume, and certain things like that. And you can do that as well and make an endless player, let's say, that always plays music generatively. I just showed you this because yesterday I was showing to one of the MDevs that they want to do something similar. But that also relates to if you want to do MIDI, we can talk about it because I have played with it sometime in the past, and it's kind of a cool thing to do. And with that, I think that my time here is over, and I let you rest. I guess that you want to take a break, and then with Edu, you keep walking.
A little bit more on the hardware side.
A little bit more on the over-the-air stuff as well. Yeah. So let's take a break. I don't know, you 30, 12:30?
Yes, 2:30.
Yeah, 12:30, and then we come back. Dun, 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 dun. Wait, this is one. Este día el ruido es brutal.
¿Sí?
El ruido es brutal.
Yo en ruido. Yo me acuerdo un poco la cantidad todo el día.
O sea, sí que le ponga. No ninguno. Solamente esa. Y ese lo vi, pero hay algo que tiene. Que bueno. ¿Qué está usando de
Un SP32.
O sea, si yo uso el código, pues, ¿qué cosa que yo lo vi? Si uso el código de eso y lo pruebo, ¿funciona o no?
Debería. Prueba con un SP con un Arduino. Prueba con un Arduino.
Sí, es verdad. Mi problema después es como el tema de cómo se hace para pasar como un código. Bueno, no, está bien. Voy a probar con más.
¿Cómo controlas esto? Vale. No, va a ser una clase más que nada hardware. De protocolos, pues ya está bien, porque si no, los pobres tíos se mata un poco.
Sabemos que hicimos con las protocolos.
No, yo con las placas de ayer todas, las metí en las cajas de amarillo. ¿Eh? Los Arduinos, los cables y los ESPs. Ah, los breadboards. Uno lo dejé en la caja esa de Turri que tenemos gris. Solo había uno grande y uno pequeño que lo metí en la caja amarilla. Solo había dos. O por lo menos cuando recogí solo había dos.
Vale, tío. Les he dicho que luego algunos los de mañana.
Vale. ¿Cierras, por favor? So, guys, let's keep going with today's class. Hello. Hello. Yeah. So this part of the class is going to be completely different, actually, and it's about, we're going to keep talking about OTA, like over-the-air transmissions, but we will not focus on the protocols and how we transmit the data and how we pair and we encode the data. We're going to go over the abstraction hardware layer of the OTA communication that actually has not the same importance as the software one, but I will say that has higher one, because if you mess up in the hardware side, you cannot fix it in the software side. It's really important. It will determine your range, the amount of data you can transmit, and if your data is going to be transmitted properly or not. So we are just going to focus on how we make the data travel from point A to point B and reach destination, and the different strategies to do it, not actually how we transmit the data. Yesterday, we went a little bit onto the different type of frequencies and frequency bands that we have, but a frequency band is just made out establishment of naming for differentiating the different frequencies. But actually, there is no a jump between any kind of frequencies. What we basically do is, let me draw, is we take the whole frequency spectrum, that the wavelength is really big, to a small one, and we basically will say from here to here is band MFF, or this one is UHF, and this one is high HF. So basically, we name depends on the friction or the frequency of the layers. And this, maybe you get some familiar with UHF. That is what usually is used in radio signals. For example, police stations usually they use VHF or UHF, but the lower spectrum, around the 300 megahertz, from usually 300 to 900 megahertz. And above the gigahertz, we call it super high frequency. For example, one of the reasons that now everybody is like at the same time freaking out, and at the same time like everything is going to change with 5G, what is the 5G. No, actually it doesn't, it's confusing because the 3G is not 3 gigahertz, the 4G is not 4 gigahertz, and the 5G is not gigahertz, it's generation 5. It works in the high spectrum frequency, but with some protocols that like they augment the bit megabits transmission. And they do it also at a higher transmission power. It's also like they say like 5G provokes cancer, blah, 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 these kind of things. Doesn't have any actually too much scientific backup because we are already using those bands, but for other users. For example, actually the TV channels transmission, the digital television uses around those bands from 2.6 to 5.9, more or less, as far as I remember. So actually what it does is they make a cutout in the TV spacing. If before we were using from 5.9 to 2.9 for the TV, what they did is cut and they just left TV here, and they included this for the 5G bands. So basically it's about band assignation, and that's also one of the reasons nowadays, like most of the mobile phones, they are like world omniscience. They can work all over in all the countries of the world. But for example, GSM bands, GSM bands, they are different, for example, in China than in the States and in Europe. So before, you buy a phone and they say, no, this phone only works well in China, or this phone only works, because the phones were manufactured to only emit or receive in those bands. Nowadays, like global economies, we make the chipsets that these devices embed, they are able to receive in most of the bands. But for example, what they consider 4G LTE, the bands I know in South Korea are completely different than in Spain. They don't use the same bands, and the phone could not have hardware support or just software support. Depends on how they program the modules. That's why when you buy a phone overseas, let's say, you need to check if it has like multi-band consideration. Depends on where you want to apply your your phone to work on. So actually, even if we use the same channel, different channels, they kind of use the same protocols, but they are using what is called channels on at certain frequencies. They will see what those are. About power and frequency transmission. Actually, this is the inverse square law. You can duplicate the power, but not even get 1/3 of augmenting the range. How you actually get longer distances? Either you increase your gain and sensitivity of your receiving antennas, or either you change frequencies. There is no other science behind it. What happened? Antennas science is super complex. It's really, really complex, and it has a super huge influence on how the hardware is designed, the material quality, and actually the purity of the materials where you make your antennas. It's not the same 97% copper than 99% copper. It's not the same having actually, for example, the boards that we use that are phenolic paper based is copper. Like the thickness of the copper of our boards, I think is like 0.1, 0.79 millimeters between those range. It's microns. And we have like 1.6 of paper base. Usually, those are FR1 PCB boards that are paper-based boards. We have FR4 that are like for example, the Arduino or like standard industry is epoxy-based substrate, has the same thickness, but the material and the density of the material is completely different. Just changing the substrate changes a lot on the antenna. So actually, for example, the paper base is less dense, is lighter. You can see on the weight that influences actually the frequency absorption of the copper layer that is attached to. Just as simple like the wavelength passes on the copper and then penetrates easier on the paper than on the epoxy. So actually there is not a little bit of refraction that the epoxy has. So actually the tuning of the antenna is different. So
what happened also with augmenting the power? For example, you can have, I just remember that in Europe is 100 milliwatts of maximum emitting capacity of any Wi-Fi device. So any router will only emit at 100 milliwatts. Shitty router will also emit, if it can, at 100 milliwatts. Another thing is the stability of the emission. You can have a device that emits a really constant power, another one that can emit with different, basically it has a DC back converter that is not stable, that influences how the amplification module. So usually all the emitting devices, they have like the input, they have the DC power converter. This guy is gonna feed your controller that is gonna produce the signals, and you will have a RF module. This RF module is really sensible. Actually, it uses its own crystal to get the frequency timed correctly. Sometimes it uses double crystals. Like, is really sensible to any kind of electrical noise. Also, magnetic interferences, because we're working with frequencies. How well you modulate your frequency is everything. And if there is just a microsecond difference, you just messed up everything. So actually, the timing of this has a master importance. So actually, these modules are clearly to see because they have a metal shield. For example, you can see on your ESPs, they have a metal casing. No? They are covered with metal compared to the 80 tinies. Why? It's a Faraday insulation cable box. So, do you know what is a Faraday box? Faraday box, basically, imagine Faraday. Let's look it for it. Cage. Oops, sorry. Let's see. So basically, a Faraday cage is a metal cage that the grid dimension doesn't allow certain frequencies to pass through. Basically, it's using a material to insulate magnetically talking of and isolating it. So usually what we know is, for example, we have some of these clear examples. We have a lightning strike. This is a Tesla coil. It produces a super high voltage discharge. Basically, it's a like thunder strike. So basically, what happened? If you have a grounded metal box, what will happen? What is more conductive? You that are inside, or the metal box around it? The metal box actually is protecting yourself from getting any kind of electrical discharge. Imagine this with way low voltage, way low amperes, and in the air, just with radio. This is something that we can see, but with radio we don't see. But it's exactly the same. What happened is we can build some Faraday boxes that they can look like this. Oh my God. So we can build this kind of boxes to actually protect from some kind and some certain frequencies of electromagnetic waves to come through. Electromagnetic wave basically is, for example, could be a radio wave. So it depends on the cage design. You can let some frequencies to pass through or other ones to not pass through. For example, a metal, let's say the cookie metal can is a Faraday box. Depends on the material thickness, will allow some frequencies to pass through or not pass through. So what we have on the ESP, for example, is a little Faraday box that is basically is a metal shield connected to ground. So that's why the shield of your ESP is ground. It's the only way to make it a Faraday box. It cannot be just a box. It needs to be connected to a ground. It insulates from any other interference. So actually the interference, what it does is it will not allow other radio frequencies to tune out the timing of your radio emitting device.
You just bounce off.
Exactly, bounce off. So why? Because this timing needs to be so accurate that in the moment we have a radio wave, it can sync or unsync a little bit the timing of your receiver or transmitter. Usually these devices are at the same time receiver, transmitter devices. So basically this is a pulse generator. This is just a pulse generator, but with really accurate timing. Is imagine a super switch clock watch that is perfect. So that's why in some electronics, you can see that you have the microcontroller and you have some traces that are basically giving information of this guy to modulate the signal based on the data you are getting. On the ESPs, for example, I just want to, this is an example of ESPs, but this, so you can actually see clearly what it is. Some ESP models comparison. Yeah, this one. ESPs, they come in different packages, depends on what is your application. Let's go over it. For example, this is the simplest one. This, we don't see any Faraday cage, or what they call it here is form factor breadboard antenna. Usually they say like EMF insulation, depends on the, well, probably in the datasheet they will say. Here we don't have it. So actually, yes, this device works, yes. What will be the range out of this guy? It will be lower. Why? Because the signal is maybe not that stable, not that well generated, and the signal degrades over the distance. If you start with a signal that is already a little bit degraded, the signal that is going to reach to the distance of another one that is properly generated is going to be lower.
You say degradation, you mean like loss of power or degradation, alteration by certain modes?
Both. Actually, it's both. You are getting less not amplitude, because amplitude is this guy, less intensity on the signal, but also like you have, for example, this is a wall. This wall bounces a little bit back and counteracts the frequency. So actually, that's degradation. Degradation is at the same time like loss of actually power and interference generated on noise accoupled to the signal. So actually, in this case, it's worse, for example, than in this case, it's exactly the same. It's an open. In case of the ESP, the microcontroller is at the same time the RFTX model. So they don't have two. This one that does everything. So you have other ones that, for example, this guy, this one has already a shielded metal plate that insulates the board. And the only part that is exposed, what is the only part that is exposed? The antenna. That is a PCB antenna. Let's go later on PCB antenna designs. So, okay, this is a really bad post. I don't like this. Models on boards. So, for example, from the same microcontroller, usually we can choose not only, well, let's view image. So this is the same microcontroller. We have different options of hardware, let's say more pins, less pins, depends on the amount of outputs, but also on how is the emitting device. This one is shielded, this one is shielded, this one is shielded, this one is not shielded, 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 shielded. Would just be the same families of the ESPs. This is the ESP01, that is basically the ESP8266, but with different form factors with more or less pins. But has like between 8 to 12 pins. What is the difference between all of them? First, shielding. Second, antenna. For example, here we don't see any antenna. This one has antenna. Let's change the color. So this one has antenna. Oh, this is not a good color. This one has antenna. This one has antenna. This one has a different type of antenna. This one, this is the antenna. This one, this is an antenna, but this is completely different. This one doesn't have an antenna, but has a connector for antenna. This one has a connector for antenna. This one has an embedded antenna. This one, we don't even know. Like, this one is embedded on the PCB.
Why is the antenna shaped like this?
Wait for it. So between the same board, we have lot of types of packets, and depends on what your application, you want to choose one or the other one. So augmenting the power, that is what everything started from, is clearly influenced by the build component quality. So for example, you can have a 1 watt emitter that has super clean output, that the transmission is properly timed perfectly, and you can have a 2 watt super noisy on the internal circuitry that actually doesn't produce the perfect signal. Does it produce more amplitude and by so more power on the emission? Yes, but the signal has been distorted. Happens the same if you want to make a comparison with audio. There is a moment that you push your speakers to the max and the sound feels distorted. That is because your amplification part, your amplifier, has been maxed out and is not producing a clean output. It's producing a noisy output. Happens the same with radio. Actually, it's way better to have a really clean and steady, lower power emission than a super high power noisy. That's why emitting at high power also has a clear influence on the maximum. These are watts. What are watts? Actually, this is translated to actually amperes. So actually, the power consumption grows exponentially. If you just want to duplicate the signal, like the range from 1 meter, distance. Yeah, for example, actually, this is well, it's the opposite. But if you are in 1 meter and you are emitting in 1 meter, if for 1 meter you need 100 milliamps, for emitting 2 meters, you don't need 100 milliamps. You need 400 milliamps. Actually, that has a clear influence on the power consumption of your devices. This power is transmitted to what? This is energy. We are emitting, translating electric energy into, you are generating radio waves. Not all the energy that you put on your board is transformed into radio waves. A lot of it is transformed into heat on your electronics. So actually, high power transmission devices usually have really big heat sinks. Happens the same with like audio. It's a similar process to audio actually, the radio emitting, because actually it's a different kind of radio signal. It's another kind of magnetic signal, but it's a signal. We produce a lot of heat. Heat, overheating and rising the temperatures, what happen again? Changes how the components work. Why? We have a line of 1 meter of copper. If it heat ups, what happened? Elongates a little bit, no? What happened when you change, for example, your antenna is tuned for a frequency? If everything gets hot, everything changes. Imagine everything internally with a lot of microtransistors and crystals that need to be timed perfectly. Again, the frequency emission changes and it's not tuned correctly. So actually, augmenting a lot the power is not that a good strategy as making the circuits more sensible or using better antennas or using better protocols. It's a solution, yes, but it's not the best solution. So actually, they sell some boards that are like signal amplifier or radio amplifiers. They work, yes. Are they actually helping you? A little bit compared to the money spent or actually the benefits on how the good quality of the signal is? might not be that good. Yes. Yes.
So why don't we transmit directly the signal? Instead of Wi-Fi SDRs, it's the main way. Then it means the Wi-Fi communication is like much higher levels, like
Yes and no. I'm in the limit that I don't know how to explain it, actually.
so then maybe the frequency is not another thing. Why do we transfer the data on this main way? Set the 1 and 0 directly or signal or
1 and 0s on the signal.
Yeah,
Hmm?
you send like square waves, yeah.
Yes. Well, no, a square wave. No, you need just analogs. Everything is analog. Everything is analog. Let me show you here. Okay, here. For example, the main signal is this, and actually you change a little bit by changing the amplitude. You change the frequency. That's a strategy. By changing the frequency, that depends on the receiver and transmission protocols and chips that you use. But before changing the frequency, changes the signal, like this, the output. One is the carrier, another one is the amount of signal. So actually the intensity. So actually this is the micro differences inside the signal. So inside each wave, let's say, you have a lower and higher margin that you can actually modulate inside.
so it's again different from what they do in AM.
Exactly. For example, frequency modulated. In case of FM, what they change is the amplitude of the frequency, keeping the same intensity. In AM, but they also are kind of changing a little bit the frequency, but that has a clear influence on the intensity of the signal. So that's why one of the reasons why FM has, like, let's say, deeper sound all over the spectrum of the sound, lower to high spectrum, meanwhile AM not. You feel that it's not constant, it's not uniform. Okay, where were we? Okay, for example, yes, building penetration, for example, 5G, like a higher you go on the spectrum, lower and worse penetration it is. You get more amounts of information in the same amount of length of 1 meter. If you cut 1 meter in the air, you get more frequency of the signals. That means more the amount of data transmitted, but worse penetration power. So actually, always that you go higher in the spectrum of the frequencies, worse penetration power you have than if you go to the lower side.
Does it only have to do with like the thickness of the material, or also
It depends on the thickness of the material and the density. For example,
lower frequencies compared to glass.
yes, exactly. For example, glass happens that is really dense material, but as it's really dense, the reflectivity of the silicates is low. So actually what happens is the glass vibrates slightly on the hardware side, on the physical side, according to the frequency. So we don't see, but everything vibrates. And actually it lets the waves pass through. Compared to, for example, a piece of metal has more denser, is way denser than the glass. But what happens is the conductivity of the metal versus the glass is lower. So actually the metal is working as a ground. Meanwhile, the metal is working as a ground, meaning that the glass is not conductive, almost not conductive, so it doesn't work as ground. So you have insulation based on the electrical conductivity and the density of the material. More denser the material for the same space, you will have more conductivity if the material is conductive. I don't know if I'm explaining myself properly. So, for example, you can have 1 millimeter of material and 1 millimeter of a glass. This one has a lot of conductivity compared to this one that only has 1. So actually, this guy will be more insulating. But for example, you can have like 3 millimeters of this guy that even if it's less conductive will have the same absorption that the other one. Hmm? The what? Exactly, it has worse penetration. How they compensate these kind of things? In case of network cells, we work with antennas that are established doing what is called cells that usually are shape of pentagons, but basically they are triangulations between all of them, increasing the amount of antennas. As simple as that.
Does it go as far as putting an antenna? I think you can do it to make sure it penetrates antenna.
Yeah, it will penetrate inside, for example, your living room, but if your dorm is behind the wall, you will still get worse signal. But it will come as close as having more antennas or more closer to you.
So the infrastructure is expensive.
Exactly. It's more expensive, not only because you need to build more antennas, but the hardware embedded to actually process that amount of data load is also expensive. And then we come with antennas. Antenna design. You're probably familiar with these guys. There's what we call a monopole or dipole antenna. That is the one that is a plastic stick. No? Okay, an antenna is just a metal conductor, as simple as that, if you want to simplify the design as much as possible. What we have in all the antennas is the connector side. This could have like a lot of different type of connectors based on the standard. We have like the neutral plane that basically everything here is grounded. Yes. And we have the active element that is actually what is actually transmitting. This is the only part of the antenna that fully transmits. And here we have a really simple rule. If we have actually it's not like that. If you want to simplify, we have a ground plane and we have an antenna. The antenna length needs to match the amplitude of the wave. Sorry. Yeah. Actually, it's something like this, and this equals to it's because it rotates in the space. The wavelength, we draw it flat, but these guys, they get three-dimensional twists. Actually, it's like a spiral rotating in the space. We represent as flat because if not, they are really difficult to represent. Radio signal 3D. Yeah, it's really weird to see the representation of them.
Wave instead of signal.
Yeah, wave. Yeah. So this is, for example, it's still a super simple approach, but this is more or less what we get in 2 planes.
Is that one there in the bottom left?
Sorry?
Is one on the bottom left marked?
This guy?
No, underneath the one.
Kind of, yep. Because they have this is in case you have an omnidirectional dispersion of the wave. That this is also another thing on top. But the waves have this. So basically what we do is a section representation of the wavelengths. So the antennas, they need to match the wavelength physically to actually be able to tune on that frequency
of the active part.
of the active part. Why is that? Because what we are doing, what is the wave and what is the wave generating? What is the wave?
I don't know.
Electromagnetic fields, no? What we are doing with antenna? Moving electrons up and down on the antenna, the same as the electrons. So basically this is moving electrons up and down, up and down, up and down. We are moving electrons up and down antenna. So actually the radio moves the electrons that are already embedded in the antenna, and with what we read is actually the, let's say, the current generated on the cable. That this is basically transmitted, encoded into a frequency that we then decompose with some protocols to get data.
Like super low frequency and super massive
Antenna. Exactly.
If you're coming to a satellite that is much, the antenna
That's why we have like the radio telescopes.
What is mobile phone that
Because we don't use that low frequencies. Actually, for example, in this device's antenna, well, in this one I know because it's quite simple. In the phone, you have an iPhone, you have a line. This is actually the length of the antenna. In this case, for example, the antenna is all the camera module around. That is tuned for, yes.
That's the maximum frequency, no?
No.
That's exactly the same.
No, it has a range of frequencies that it can listen to. But let's go for different types of antennas. We have a lot of antennas. Antennas designs depends on how you want the data to be received. What is the direction that you want to receive the data? And how sensible you want to be the antenna to be. These are some antennas. This is a circular polarized antenna. This is a circular polarized with a different package. So these antennas are really similar. And this is a dipole antenna or monopole antenna. Let's close this. For example, this is circular polarized antennas. What would change the geometry of the antenna based on what? First, on radiation pattern and sensitivity. The radio waves are in the air, floating, like you want to say it, vibrating in the air in all the directions. But the same as we have ears that are oriented, we more or less listen in 270 degrees. We don't listen really well on the back. We have a sound pattern that we can listen with more intensity than in the back one. So actually, a human being, if we have the head, the sensitivity pattern of our ears in flat is something like this. Happens the same with the antennas. And this is about directionality, omnidirectionality. We have this radiation pattern of antennas. So for example, the standard plastic antenna that you are familiar is a monopole, is a donut. What? Has a donut shape. So actually the antenna is not sensible in the top. So actually there is a really mismatch. A lot of people think, hey, I don't get coverage. I will get in the antenna because it's where it's pointing from. Actually, this is the worst location that you can be. It's way better to be exactly on the straight side, on the perpendicular side. So that's why, for example, a lot of routers, they have different antennas. For what? If this antenna is producing a donut like this, and we put another antenna in a 90 degrees angle, we will produce a donut that covers this area. And if we do it in the other direction, what we get? A perfect sphere. So actually, the antennas, if they are in the same for the same frequency and everything, because sometimes you can emit it with 3 antennas at a time, not all the devices can, you tune them at 90 degrees to get the maximum coverage, to get full omnidirectional coverage. That's why, for example, if you are, I don't know, you are at 100 meters and your antenna is pointing to you and you're not getting range, maybe just making it strictly perpendicular, you might get a good connection. So depends. Depends. If your router, both antennas are for the same frequency, they are supposed to be at 90 degrees angle. If they are from different frequencies, in theory they should be parallel. But the physics says that they actually should be slightly tilted. So actually they don't create interference to each other. Exactly. So if you have your router that is more or less modern, emits will be one for 2.4 and 1.5.8. So actually we try to tilt the emitter lead so that actually they don't get full conflicting frequencies to each other. Why? Because it's double amount of frequency one of each other. So basically we will have something that is, okay, this is really difficult to draw, but is double amount of frequency. So actually this might get a little bit of interference of one layer on the other one. So if they are not exactly in parallel, it's better. Then we have yes, and the ovni is like actually a ovni. It has like a weird shape like this, like a flower. Yes, a patch antenna, for example, usually is what we call GPSs. If you have seen that GPS is a square, that's actually is a patch antenna that has a similar wavelength radiation pattern as, for example, our human ears, because it's designed to work in a huge direction. Yagi antennas that are the typical TV antennas of the houses, they are actually meant to work in only one direction. So actually imagine like a drop of water three-dimensionally. They have a lot of sensitivity in one direction, and they have a little bit in the other ones, but have none in the back. Hmm? The ones that are just a pole are these guys. The ones that are like the little metal grid that is three-dimensional like this. This is a Yagi antenna. Really directional. That's why, for example, you need to tell the technician to actually orient the antenna properly, because a little bit of tilting has a great influence on the range, on the reception. Yes.
How do you need a single antenna to make MQTT and differentiate between listener and
Good question that I don't know how to answer.
That's what you do with Wi-Fi models.
Yes, the antenna has dual purpose, yeah, emitting and receiving. Actually, I don't know how they do it. It's everything is in the receiving model. So, for example, the antenna length is calculated by the frequency. For example, this is a 1.2 gigahertz, and this is a 5.8 gigahertz antenna. This measures 2 centimeters. This measures 20 centimeters almost. So that's why, for example, why the antennas of the house are big, because the TV's emission channels are low. Why the phones, we don't have a super huge antenna, because the emission is low. Actually, I can show you if you give me a second.
But what phones do have super huge antennas?
To augment the sensitivity.
Satellite phones are antenna.
Yes.
No way.
Yes, because the frequency is different of emission, of reception, or no, emission, reception, both. I'm looking for a picture. Just now. Well, actually, maybe I can look in. Um, this is a particularity that I was like super amazed when I went to Korea. Korea, well, you know, like they have LG, they have Samsung, they have like some of the high techs. They get used to have TV on the phone. And before the rise of the 4G internet, having video on live, it was not that common. Like 3G, you cannot transmit full video everywhere. So actually, the phones in Korea had TV embedded into them. What happened? The TV transmission of the frequencies is different. So actually, nowadays, no, since like 3 or 4 years ago, no. But until 4 years ago, all the phones in Korea have a antenna that you can take out so you can actually receive. For example, exactly, phones, they cannot receive AM and FM modulation. Actually, they don't receive AM. I think they only receive FM. Why? Because they use the headsets, your headsets, to actually use as an antenna. Yes, that's why you cannot receive radio if you don't have your headset connected, because they use the capacitance of the headsets as the antenna. What? No, different frequencies. And in case of the TV, as you are getting video signal that has much higher byte rate, you need to have a specific one. It's not that sensible one. So we have monopoles. What is a monopole antenna? Here we can actually see this is the active part of the antenna, and this is the non-active part. What is the difference? Do you know what is a shielded cable? We have a metal, and we have usually a plastic sleeve protecting the metal, no? On cables. A shielded cable has another layer of metal around, and it's a cable inside a cable, and a piece of plastic protecting the other cable. And this one is ground, is negative. G and D. So actually, this is what is called a coaxial cable. It's a cable in a cable or a shielded cable. And we use them for antennas. Why? Because this will be our passive element and this will be our active element. Can we make directly a microcontroller like the receiver TX module directly with a piece of cable attached to it? Yes. The antenna could be directly attached to the module. There is no problem. But what happens, for example, when you don't have a space for it? You need to move the location of the antenna. You need to move the antenna to another location that has better connectivity. No, in that case, you need to have all the antenna protected so it doesn't get any electromagnetic interference from any other devices until you get to the correct location, and you just show your active part of the antenna. First case. Second case, in antenna design, the length of the passive has an influence on the sensitivity. So actually, the passive, as I don't remember these numbers because this is really complex, like theory of antenna is really complex, but needs to be at least 1/4 of the length of the active. And with that, you duplicate a little bit the sensitivity, but enough to actually increase a lot the range. So actually, huh? At least. I don't remember these numbers exactly, but it has a clear influence. So this is a monopole antenna that is almost the most basic one. That is the simplest one to manufacture. For example, here, this is a monopole antenna, but you see this metal shield cover is to actually augment the capacitance of the ground. This has another measurement that you can increase a little bit here then to also increase the sensitivity. So there is little tricks to actually augment slightly the sensitivity. In here, we have the capacitance of the ground, that the shielded cable, and we have an extra add-on to increase the sensitivity. And then we have the antenna. Usually, you go with some charts and the cable length and the antenna calculation is usually is not the same size of the frequency. And this is where I'm gonna get you completely crazy. Before we were saying that the antenna length is for matching the frequency, no? No. Is we use half of the frequency or 1/4 of the antenna length, because with the 1/4 we almost get the same as the full, but 1/4 of the size, and with the half we get almost the same as the full length. What happened? We just need a smaller size of components. If an antenna, for example, at 2.4 gigahertz, this is a 5.8 gigahertz antenna, measures 11.71 millimeters. If you make the full range, is you get 22. This is half of it. A full radio signal antenna for 5.8 gigahertz is almost 50 millimeters, 5 centimeters. You're becoming like something that is not easy to embed everywhere. And you asked before, why the antennas in the PCBs, they look like this?
Oh, what is it, like the length?
Is the length. Because if not,
You take the length, like the length of the, like each.
is the frequency that the antenna is tuned for. Of course, this reduces the sensitivity of the antenna, but we get a lot of complexity of the antenna design. And this is not as simple as just twisting the wire.
So the small wire is the active part?
Is the active part. What happened in here, it matters a lot, the spacing between the elements and also the spacing of the copper. So an antenna is as simple as cutting a wire on the size, but as complex as measuring microns, putting a capacitor, like putting ground, making a shielded, making double shielding, like this guy. There's a lot of things that increase a lot of sensitivity, but making the simplest simple antenna is a wire cut up to size. Why you think there are antennas that they look like this, like a coil? It's the same. Because, for example, a 400 megahertz antenna measures around 12 centimeters. 432 Arduino MF. For example, these guys, that if you open anytime a remote for a TV or like not TV, like door garage key or something, they have this. Why? These usually devices they meet at 433 megahertz. The antennas, if you elongate this, they will measure something around 15 centimeters. You don't want a remote of 15 centimeters. So actually what you do is you produce a spring to have the same length of the antenna, but in a smaller package. Are you reducing the sensitivity of the antenna? Yes. But you get the cost of you can't fit it everywhere. Okay, let's clear this, clear all drawings. So, and we have half dipole antenna. That imagine that you have like two active elements, and they measure 1/4 and 1/4, and they add half of it. These antennas are not quite widely seen because actually they use a lot of space. But the most standard antennas are these guys. They're like the dipole antenna.
Doesn't the plastic affect also the sensitivity?
Yes, a little bit. But in general, plastic, what we use so much is because it's almost transparent for radio frequencies. For example, we have helical antennas. That is the one that I will show you. It's compromising having an helical antenna. It's a long cable, but roll around an element. In this case, we put a big ground plane to have a really passive element that isolates. These antennas, as the wavelength is bouncing here and coming here, usually have a radiation pattern that is directional. So actually, for example, let's say your Wi-Fi is in the corner of your house, you can actually change your omnidirection. If your house is a square and your antenna is located here, and you have a standard dipole antenna, what happens? You are getting something like this in plan view. You can change the antenna or a patch or a helical and get a coverage that is way bigger in this direction. And you don't get signals to your neighbors, for example. We have patch antennas that are the ones that they are clearly seen for GPS. Why we use patch antennas that are super directional? How we use a GPS in general? What are we pointing at? The sky. Exactly. So a person is here, and we want that the satellite that is really far away, we increase the sensibility. As simple as that.
If you build the patch, you get a more.
No.
No.
No, no, no. No, it needs to be flat. Yes, that's they do in phones. If you ever look at phone cells, towers, like usually they are like, let's just look at picture, it's easier. What are these guys? Lot of patch antennas in different directions. Because you want to transmit in some certain directions to get different. Basically, these are big elongated patch antennas. Then we have the circular and like the plate antenna that is really, really directional, that we will focus. Actually, in the antennas, something that is common misunderstanding is that the antenna, this is the sensing part. No, actually the sensing part here is this. In this kind of antennas, we have a CAN, and we have the active element here. What we do is we concentrate the radio waves to be bounced from multiple directions into here. And we have this CAN, so actually this CAN bounces back the signal and gets into the active element.
Isn't it like a whole circular shape of the antenna? So
yes.
Yes.
Arrecibo antena. Arrecibo. ¿Es arrecibo? Arrecibo. Yeah. This is basically. These are metal plates, and the antenna is actually here. And what they do in this satellite, in this observatory, is actually these cables is because they change the position of the antenna to from here to here to actually accommodate, depends on where are we pointing at. We don't change the dome, the disc that is huge. What we change is the other part. That actually right now is like this. Was a big. Actually, one of the cables broke and the antenna fall into the panel. Is it already inactive? No, it was inactive, but actually it has been like this. It was in this radio satellite is old, but it still works quite well. It's really sensible, but it doesn't have as many features as the other newer ones. So actually it's dedicated for the SETI. SETI is the Department Worldwide Consortium of looking for extraterrestrial life. And this usually don't get really high budget. Happens this accident, and they say, okay, we need to close it down. But there was a like big crowdfunding campaign, and a lot of people like, wait, guys, we need to fix this observatory, and I think they are going to fix it. But everything is like in the like nobody wants to put money, but everybody wants to make it work. But like people don't, like governments don't want to say I spend like half of the budget on fixing an observatory to look for aliens. That is what people get. So we have range, power, and dBi gain. dBi gain is the sensitivity of the antenna. More sensible the antenna is, usually we have a flatter radiation pattern. So for example, let's go with a simple example. We have a flat monopole, dipole antenna. A dipole antenna has a radiation pattern more or less like this, no? This is, for example, a 3 dBA pattern. if we have, like we'll draw it here, the same antenna with more sensitivity, we are getting more range, but we are also cutting down in other directions. So a higher dBA antenna, yes, gives you more theoretical range, but you are losing, for example, all this side of the antenna, of the reception. So actually they gave a flatter radiation sensitivity pattern. So usually something that is really easy to change is, for example, in Wi-Fi routers to have a house applications is you can have a 1 dBA antenna, shorter range but really omnidirectional, or the higher gain antenna. For example, a 10 dBA antenna usually is slightly bigger. That will be a really flat. That if you range the antenna correctly, gives you more coverage, and you don't waste network on the top and the bottom neighborhood. So you can play with power, range, and dBA gain. That is basically the sensitivity of the antenna. And usually the antennas, they give some these maps, horizontal and vertical, to see what is the radiation pattern of the antennas. And usually when you have an antenna, they say certain frequency, what the antenna is centered for. This antenna is tuned for 5.8 gigahertz, but even so, these antennas are usually given to measure between 5.6 to 6.2. They have a range of sensitivity, but they will have the peak of sensitivity at 5.8 in this case. Yes, is where they have the most, and they will have like on the lower side and the higher side of the spectrum. It doesn't have to be symmetrical, but it's a higher peak. And they say the gain, and also the bandwidth. Actually, in what is the maximum and minimum sensitivity between 5.5, I was not really far away actually. 5 point is, for example, this one has on the lower side than in the maximum side. So when you choose antennas, this is quite important. And the radiation efficiency is like the amount of actually watts that you transmit into power in the air. We have, well, this is about really complex calculations. These ones you have calculators to actually get ranges, depends on the frequency, transmission power, antenna gain, antenna reception gain, sensitivity of your DRX sensitivity is like the receiving module sensitivity. So when you have a microcontroller, they will state the power in watts or dBMs and the sensitivity also in dBMs. How sensible is the receiving module? Nowadays, the receiving modules are getting so sensible that we don't need to increase the power. So actually, we are not consuming more. What we are doing is being more efficient. And we are doing every time better and better. Why? Because everything is about timing on how you tune your frequencies. And we are, right now, for example, to give you an idea, Arduino has been here for more or less 15, 20 years. It's a 16 megahertz. The ESP, how many megahertz is that controller? 240 megahertz. It's more than like 12 times faster. Happens the same with the transmitting and receiving modules. They are better and better and better and more efficient. And understanding antenna gain. So if you want to look at flashlight or sound, this is actually the difference of the gains of the antenna. So actually choosing an antenna is quite simple. Depends on basically on your application. And they have these radiation patterns. So bandwidths. We are working with frequencies. So we have to choose, for example, a certain type of frequencies. For example, we say that Wi-Fi works at 2.4 gigahertz. That's a lie. It's a way of simplifying things. Wi-Fi works, at least in Spain, between the channels. Well, I'm not going to make it up. I'm just going to look for it. Wi-Fi canales, Wi-Fi España. Actually, we have 13 allowed bands that range from from 2.412 to 2.472. And this is what we know channels. The TV has channels. Why? Because between the same frequency, we have small frequency variations, slightly lower and slightly higher. And when you change the TV channel, what you are doing is synchronizing these guys. And between channels, we have overlaps. This overlap is really important and is based on the emission spectrum. So even if you tune to emit at 2.495, when you transmit, you are also transmitting in 2.4, actually 2.50 and 2.490, a little bit, with less power, but you are still transmitting in those range, because we cannot just stay to have a super frequency. We cannot be that accurate.
So you have offset now.
Yes, a little bit of offset. We transmit slightly higher and slightly lower. That's why, for example, it's really easy to see in the radio. Sometimes you tune a TV station as a radio station, and you can hear two stations because you are in the middle point. That both actually are getting enough, more or less the same power, and the receiver module of the radio doesn't know, actually mixes the signal because it thinks it's the same signal.
Like if you have multiple Wi-Fi networks in the same area, the data overlap.
That's, yes, exactly, and this is what happened nowadays. And this is about channel selection. So routers, what they do when you connect routers, most of the devices that they do this automatically, they scan the whole band. They see, I see a peak of emission in this guy, a peak of emission in this guy, and a peak of emission in this guy. So based that I know how am I know that I emit better in these channels, this channel, and this channel. I'm going to look automatically for the more efficient channel with less noise to emit my channel. This is what Wi-Fi does. Actually, what happens if you live in a high-rise flat? You have a lot of channels really polluting, and there is no space. What you have to do, basically, is emit in the same channel, but try to emit, you are just overlapping the signal. That's why, for example, if you live in a really high density area, your Wi-Fi goes slow, even if you have a really nice network connection. If you are transferring to the air and there is people, it's like living in the same living room and having one people speaking as we are, or we have the four of us speaking at the same time. It's impossible to understand anything. If you have four people speaking at the same time, it's really impossible to understand. Unless, what? We augment the power, we shout, or you make it more directional, you only point at someone, or you are really smart and you are able to focus on only one people's speech. That usually that's what's difficult and what actually reduces the amount of data you can transmit, because data gets mixed between the different frequencies. So actually, the easiest way to increase a range is actually look for the cleanest channel.
Sorry, that's another question. But say if you do Wi-Fi network with your Esp, it doesn't have this feature automatically.
Yes.
It does?
Yes.
Oh.
Yes.
But you could do it manually.
You can do it manually. You can override. And actually, this is the legal spacing. These are standards that the minimum spacing between channels in this case is 0.00 hertz, like gigahertz. So we need to have a minimum spacing between channels of this, so the channels doesn't overlap. So actually the channel exists, because if they are too close, it's like being emitting the same channel. So depends on the band that you are emitting, you have channel spacings, bigger or lower. Also depends on the amount of data you transmit. You have bigger spacing between bands or lower ones. These are the standards, and usually you have like channels, list of channels certified by country to accommodate that everybody can use everything. If they all are 2.4 gigahertz, yes, because they only can use 14 channels. So actually, at least 2 of them will have the same channel. For example, I do it quite each 2 months at home. What I do is a Wi-Fi scan. You can download apps for it, and they show you all the channels and the power emission of each one in dBMs. I just look for the cleanest spacing or the one that has the less power in my area to emit on top of that one. Actually, these are, for example, access point, channel ratings, channel graphs. So, for example, here, this is the emission of the channels. And this is in 5 gigahertz. Let's go to 2.4 gigahertz. Actually, we have overlaps of 6 channels. It will be really smart to use the space between. Actually, what happened is like the companies, the routers, they have pre-programmed and they say like they give you like same router for everybody. So actually, common issue is like standard routers. If you don't configure them, they always emit in channels 3, 6, and 9. They don't use the other ones. So it will be as simple as, okay, I just changed mine. And usually it's like you have NTA bands to work. And you can increase a lot your speed with like that. So usually city looks something like this. And basically it's a fight of people and emitting frequencies to see what the data transmitted. And here is where the protocols takes a huge importance. How you reassure that your data is being listened and transmitted properly, that even if you have noise and maybe some packets are not being received, you can resend them to be able to get the proper connection or the data transmitted correctly. And for example, these are channel frequencies with the higher and lower bands. I usually have table charts like that.
Is it the same with 4G, 3G, 5G, all these?
Yes.
But they have a wider spectrum.
Yes.
That's the combination of the devices that you network.
Exactly. So this radio jamming is producing a signal that is exactly the opposite on the frequency and power to actually erase the signal. So if you emit a wavelength, you can do 2 types of jamming that is producing the opposite wavelength, exactly the opposite. That will produce a 0. It's pushing to the right, pushing to the center, to the right, to the left, 0 forces, or producing so much noise in everything that is impossible that the receiver listens anything. And this is what actually, for example, the drone guns, actually shut them down. What they do, they don't shoot anything. What the drones work on? Radio. It's a high directional antenna with a high emitting power amplifier that basically emits in all the frequencies that usually drones uses. And for example, if you have like, I don't know, the president comes by, usually a police car passes 5 minutes before. It depends on the country. In Spain, they do. Because we have terrorism. So actually, sometimes the Wi-Fi get disconnected, you lose the power.
In Mexico, we're using some like bazookas. They were like throwing these signals, so they can.
So actually, a lot of police cars, especially in demonstrations, this kind of thing, sometimes they say, I get low coverage. First, a lot of devices connected using the same frequencies. Second, they might be each hour or each 2 hours jamming everything for 1 second, enough that everything disconnects and reconnects. Why? Because bombs in general, they use radio frequency to get activated. So before the connectivity of bombs like this, they are paired. If you unsync them, they are not able to pair again, so they are not able to explode the bomb, or just not explode meanwhile the president or someone important is passing by.
Yeah, there's a lot of associations with bombs. And I was working in a bank near resistors are, resistors are, sometimes it has that, everything is shut down.
Yeah.
Wi-Fi, phones, and that only 2 minutes before we said.
My school too, like my university was close to the to the president, and well, but like my house is close to the president or like VIPs, and also to the king. But the next time the helicopter of the king passes by, everything out. And then we have antennas, connectors. That these ones are important, but not that important. They have an influence on the antenna, but basically you need to know what type of antenna and how it's named, so you can actually choose for your connector. There are two types, SMA and reverse SMA. Basically, it's like this. You have SMA that the male has a female, and RP SMA, actually this is wrong, it's RP SMA that the male has a male. It's the opposite internal connector. Do they have influence? No, but you need to connect the male inside the female. That is actually, this is the active part. The exterior, what is? The ground and the isolated part. So if you connect this guy to this guy, you are not connecting the active parts. It's quite important to choose the correct one. And then we have the UFL connectors, that is the connector for connecting for PCBs. PCBs, having this connector on a PCB is bulky, is heavy, and usually a SMA connector for PCB is when you have a direct connection and needs to be quite strong. For example, a Wi-Fi router, or that is something that people uses without any care, connects the antenna and puts it on maximum torque, uses these guys because they have a lot of holding part to actually be quite strong. Meanwhile, when you want to save space, you try to use UFL, that is a little clip connector. And you have a newer generation that is the MMCX connector that has the best of both worlds. What happened with this guy? This is a clip. It's really easy to unattach it, but actually it's in phones. Well, phones no, because they use PCB antennas. But laptops, if you open a laptop, the Wi-Fi module is really easy to recognize because it has two connectors of this and a big Faraday cell metal box around it to actually protect it. We have MMCK connectors that are clips, but they also load 360 rotation, like, oh, sorry, 180 rotation in the axis. It's quite nice. It's like a SMA, but you don't need to twist, they just clip. And for example, this is a receiving module that has a big ground plane and a connector. Then we have polarization. That is something that I will not go over a lot, but and it's only for a certain type of antennas. That is something used when you cannot change the channel, have to emit in the same frequency, and there is no other option. So you can polarize your signal. For it, you use these antennas. So it's impossible to draw this into the. Yes. So in a linear antenna, the signal more or less gets flat, stable in the space. A polarized antenna, what it does is the wavelength rotates three-dimensionally, for example, to the right, to the left. And you can produce the same signal rotating to the right. And you do this with antennas and the antenna design. So actually you are able to transmit in the same frequency, but the signals cannot be accouplated to each other, synced, because they basically rotate in the opposite directions in the space three-dimensionally. This is something that you use sometimes when you have another choice or you want to transmit in the same channels, and you do with antenna design, that these elements, they rotate to the right, or they can be the opposite, rotate to the left. And this produces radiation pattern turn. You are basically rotating the wavelength at the same time or rotating the opposite one. This is just, I want to mention that exists, and it's about antenna polarization. And in order to receive that signal, you need to have an antenna that actually rotates, is polarized in that direction. So a right polarization cannot receive a left polarization. Actually receives, but with worse quality. SMA, and for example, here the ESP 10 kilometers using a proper antenna. Of course, the baud rate of transmission here is low. The amount of noise is high. You need to clean a little bit the signal, but everything is on antenna. Properly oriented antennas, good design antennas, good insulation of your electronics matters a lot, but has a huge impact. That's why any router, you don't have directly the AC connector. Why you have the DC power supply and then the DC connector to it? Because the DC transformer, AC-DC, makes a lot of electrical noise. As simple as that. It's never embedded in the same device. Produces a lot of interference that we don't want. So, for example, here we have some examples of different radio frequency devices. For example, the NRF is a module that we use for Arduino that transmits into 2.4, 2.5 gigahertz, but actually uses his own protocols, but uses the same frequencies for emission. And these guys, for example, we talk with I2C, with SPI to talk with them. We connect with SPI, and they tune themselves the frequencies, and they pair to each other on their own. Yeah, we have a lot of them. They look really similar to the ESPs, but because they took the same package design, but they are not. How you can improve this? For example, if you measure this antenna, this is a 2.4 gigahertz antenna. You can cut this, solder a cable, a straight line cable. Just by that, you have increased the range. Actually, last year, well, 2 years ago, what we did is today's class we also run on Fridays because Wednesday class was smaller. So what we did is basically took antennas, Wi-Fi's, and with IKEA cans, like the trash cans that are metal, we just cut by half. This is a super huge antenna, directional. And we also use Coca-Cola cans. So actually the students use these guys and they cut a Coca-Cola can in half and they put the module here and ground it to the can. So actually they were talking to each other just by orienting. They only listen to what they want to listen just by orienting the antennas. Or you can just isolate it by just putting a metal cover over them. They are really directional antennas. So actually you have this sensitivity on only some areas.
And they each like tune to one frequency
for the same frequency. Same frequency. For example, we have the HC2 is a half duplex. That means we can talk and transmit at the same times. For example, this guy is not a half duplex. Is what is called transmitted receiver. Can only transmit but not receive at the same time. So, for example, that's what I say. How you transmit and receive the same antenna at the same time? That depends on the microcontroller that controls the reception. Some of them are only able to transmit. They don't listen meanwhile transmit and then receive, like wait for a packet. When you have like both at the same time, it's called half duplex. Half duplex is they're able to do both things at the same time. Receive and transmit with the same antennas. So this guy, huh?
Isn't there something called full duplex?
Don't know. So for example, this guy emits in nothing, like 100 milliwatts, the same as the Wi-Fi standard, but uses 400 megahertz frequency, and just by that, it reaches 1 kilometer. And this is the shittiest thing ever. Like, it's a piece of metal attached to. You can just cut a metal cable and attach to. Of course, the metal conductivity matters a lot. So actually, for antenna design, you want to use pure copper. If you buy somehow you want to test, we have like a box of copper, pure copper cables with different thickness. The thickness also influences the sensitivity. Usually, you want to use as thin as possible. And then, well, we have Wi-Fi broadcast that, for example, are some if you're interested, some projects that they are uses the Wi-Fi protocols, but not to transmit data over Wi-Fi, but to transmit full HD video. That is something that is quite complex, and actually that's a huge deal on the market. That is before was only mostly used for resonance, like medical resonances. The technology on how to transmit the image from the machine to the receiver station is usually wireless to actually avoid noises on the machines, etc. So actually, how to transmit it is difficult, and a lot of people setting a lot of money because its medicine is a great business. So that means like the full HD transmission of wireless video really complex. For example, one of the deals of DJI, I don't know, the drone company that sells drones, is really famous over the drones that everybody has a DJI nowadays. Has a drone. Most of the market is DJI. Their business is not only not the drone; it's actually they encoded how to use full HD video transmission without packets losses. That's their business, and that's actually what they sell and they work for. The drone business is a huge business that they are going through it, but it was not the deal. It's actually in the moment they got full HD video transmission without packet loss and buffering of data, repetitive data. So if you get a packet, you still get full HD signals. This is their business. And that's it. Questions?
Yeah.
I suppose lots. Yeah.
If you're using like specific protocols for over the edge, such as the Wi-Fi, could you maybe not do like the jamming, but pollute the whole spectrum?
Yeah, there are projects to use the ESP32 as a jamming device.
And if you just pollute with something specific and you send something specific to the device.
That depends on the protocol, a lot on the protocol. In case of jamming, in general, what you emit is on most of the bands.
What?
You emit in general in a specific band or all the bands, and you just send a lot of data at maximum power. In general, but jamming is like, I never went really deep into that. But in general, generalistic approach is that one.
When the way the data is being encoded at five times the way we send the data, or that it also means the way we translate the data and
How we translate the data.
Yeah.
Actually, Wi-Fi is a protocol of communication that uses 2.4 gigahertz. But what happened is like we say that it uses Wi-Fi. We have simplified as is 2.4 gigahertz. But actually, there are a lot of devices that emit 2.4 gigahertz and they are not Wi-Fi. It's an abstraction, yes. Like saying, I don't know, instead of saying robotic arm, you say KUKA. Everybody will understand you. Like, it's actually all the KUKAs are robot arms. No. Are all the robot arms KUKA? No. But for example, like a lot of devices emitted Bluetooth is 2.4 gigahertz. And we don't say, hey, you are emitting in Bluetooth. Bluetooth is actually a communication protocol that uses that band.
It's all structured. It's like now I have like the model of devices, IP address. There are a lot of things identify who is the what. Where you try to so you're sending a chain of bits. This chain of bits has a structure to it. So first 8 bits to this, second 8 bits to this. I think it's
for example, this guy, this is this board uses serial to connect through it. Yes. This we can use it as transparent bridge. We call a transparent bridge. If you connect another guy in the mirror, this is a serial connection and this is a serial connection, no? If these guys, you don't have to code or emitting or say what kind of communication protocols and how they encode the frequency to the communication message. In here, you sell to the serial monitor a 1, and these guys receiving the serial monitor at 1. Actually, the hardware layer is transparent for you. It's what they call a transparent bridge in OTA. So OTA modules allows you to do this, or you can configure them to do this. Not all of them, but especially I use these guys because I'm not good at coding. And most of the times I just want to say like simple data, like zeros, 1, 2, 3, 4, like, and with a serial communication that I'm really comfortable with, and just put these guys, connect, nothing to do. Transparent bridge. Super fast. What happened? If you're sending the message, the one might not have listened. How do you confirm that the message has been acquired properly? That's basically the communication protocol that you need to embed on top. How do you confirm the messages between each other? So, for example, 3D printers right now, we have the motherboard that controls the motors, no? The screen, what it does has a SD card. The SD card, in this case, is Esp protocol, and it's not actually reading directly by the controller. The Esp is reading by another controller that is in the LCD screen holder. And these guys, they actually communicate. I'm not sure right now, but I think it's I2C. So actually, to get a communication between them, to get the files ready, they read by SPI, then I2C, then go to the board. If I connect my computer, this link can be established. I connect with serial TTL, basically, that is FTDI. So actually, from my computer, I'm able to go through the serial, go through here I2C, read through SPI, and read the SD card and write files into it. How these guys can check that the communication is properly done? It's serial, it's a quite basic connection. They use echoes. So for example, if you are sending a G code, usually has lines of codes, no? This guy sends line 1, and this guy answers line 1 read. So in the moment we have line 1 read, this one sends line 2 read, line 3 read, line 5 read, line 6, line 7, you say, oh, line 7 read. Okay, I resend you the line 6 and stop the things until you do the line 6. So that's everything is a layer of code that you need to embed.
It's a mess. So many protocols.
Yeah. That depends on how, let's say, armored you want the protocol to be.
How armored?
Armored. It's not the same. Moving to give you an idea. One thing is reading a sensor of a humidity sensor in a rooftop. Another one is these guys, the industrial ones. This one lifts 100 tons. It's a completely wireless robot. If you miss a package of this, you can, it's a big mess up. In that case, you use protocols that are really, really armored. So that actually there cannot happen any data loss. And you embed, on top of that, you embed safety protocols. But there are some applications like military, like the president, like the typical, opens the suitcase and launches a missile. It cannot fail. Well, it should fail, but that's another thing. But some things cannot fail directly.
Yeah.
That even so, they fail. Yeah.
I hope
Yeah. Mo, do you have any questions on remote? You were really quiet.
Maybe one question. If I plan to use 80Tiny85, do they have I2C?
801085, I think, yes.
Yes.
Yes, the 85 or the 45?
85.
80Tiny85.
Yeah.
In out, I think, yes, like the I2C is like the super basic protocol, like they embed.
Yeah, I think it said something like TVI, two-wire interface. Is that that? Is that the thing?
PC, ADC, SCL. Here is SCL, that is clock line.
And SDA.
The SDA here. Yes.
Yeah. Okay,
Yes.
so if I want to connect
Here, SDA and SCL.
So,
For example, the 80Tiny families, you program them through SPI.
Yeah.
So
Okay.
they have that connection.
Okay.
And I2C is really like the two basic connections that all the microcontrollers have. Most of the microcontrollers, for example, the Tiny family doesn't have a serial.
Yeah, yeah.
Soft serial.
Yeah, and I need to use soft serial. Yeah. Okay. Thank you.
Someone else? No? Okay.
What is the maximum range you could get with one of those chips you have want to make that? Just for fun of
LoRa 100 kilometers.
So this is what we have here.
Omnidirectional.
Omnidirectional. Depends on the terrain and these kind of things, but
On flat terrains.
yeah. For example, here we have a LoRa station on the roof that is basically a super small module. LoRa's are not really expensive, $30. Therefore, what they are amazing. We have an antenna that is it's a big antenna, but it's not crazy, like 1 meter. We use it to communicate with Laura, the campus that is on the top of the mountain or the other side of the mountain. They used to communicate like that. Now we don't use it, but it's in case somebody wants to use it. Huh? Well, Morse code is really simple, like super basic data. So actually, you can reduce the bandwidth, and that's why Morse code is Morse code, because you don't need to send a lot of transmission data. So actually, you can reduce the baud rate. You are reducing the baud rate based on the fix. That is your baud rate. Okay, so for lunch.